Imagine holding a solid sphere in your hands, feeling its weight and perfect geometric form, and then consider this deeply unsettling mathematical truth. This sphere can be divided into a finite number of non-overlapping pieces that can be reassembled, using only rotations and translations through space, into two spheres that are identical in size and shape to the original, each possessing the same volume and density as the whole from which they came, and this process can theoretically be repeated infinitely, creating boundless matter from nothing through the pure mechanics of geometric rearrangement. This is the Banach-Tarski paradox, discovered in 1924 by Stefan Banach and Alfred Tarski, a mathematical statement so fundamentally at odds with our intuitive understanding of physical reality that it seems to violate the most basic laws of conservation that govern our universe. The paradox emerges not from any sleight of hand or trick of perception, but from the rigorous application of set theory and geometric principles, specifically the ability to decompose a solid sphere in three-dimensional space into a collection of point sets that, when reassembled through rotation and translation alone, can create two complete and identical spheres where only one existed before, with no material added or removed, only rearranged. What makes this paradoxical is that the pieces themselves are not merely difficult to imagine or visualize. They are, in fact, so fragmented and scattered through the dimensional space that they possess no well-defined volume or measure in the traditional sense, existing as infinitely complex point clouds that defy our ordinary geometric intuition about what constitutes a measurable, bounded object. The mechanism that allows this apparent violation of conservation lies in the nature of infinite sets and the properties of rotation groups in three-dimensional space, where certain collections of points can be rearranged in ways that create new volumes through exploiting the mathematical structure of the underlying space itself, something that cannot occur in one or two dimensions but becomes possible only in three dimensions and beyond. Imagine a mathematical object so peculiar that it possesses properties which seem to violate the very foundations of geometry and intuition, a shape created in the 17th century by the mathematician Evangelista Torricelli that exists as an infinite surface, yet somehow encloses a finite volume, and this contradictory nature has fascinated and troubled mathematicians for centuries as they contemplated its strange implications for the nature of space itself. Gabriel's horn, named after the archangel Gabriel because of its supposed ability to hold enough paint to cover its infinite surface, yet simultaneously contain a finite amount of liquid, is constructed by taking the curve of 1 over x, beginning at the value of 1, and extending infinitely outward along the horizontal axis, then rotating this curve around that same axis to create a three-dimensional form that tapers infinitely into the distance, becoming thinner and thinner without ever actually closing or touching itself. The paradox emerges when mathematicians calculate that, while the surface area of this horn stretches toward infinity as you trace it further and further into the distance, the volume contained within its walls remains finite, a bounded quantity that could theoretically be filled with paint or water, yet would never be enough to cover the exterior surface, creating a logical impossibility that haunts the boundary between the infinite and the finite. What makes Gabriel's horn so psychologically unsettling is that it challenges our fundamental understanding of what objects can and cannot be, since our experience with real-world shapes tells us that if something can hold a finite amount of liquid, surely you could pour that liquid out and use it to paint the exterior. Yet mathematics proves this intuition fundamentally wrong in ways that our minds struggle to reconcile. We have normalized this paradox within mathematics by accepting it as a proof of concept about the peculiar nature of infinity itself, understanding that infinite surfaces need not require infinite volume, and that our intuitions about scaling and proportion break down entirely when confronted with truly endless dimensions. Yet still the horn persists in our imagination as a disturbing reminder that the universe operates according to rules that contradict our deepest spatial reasoning. Imagine taking a simple paper strip, perhaps 1 inch wide and several inches long, and performing the most mundane of actions, giving it a half twist before joining its two ends together with tape or glue. What you have created is not merely a twisted loop, but rather a surface that defies one of our most fundamental assumptions about how objects should behave in three-dimensional space. When you take a pen and begin drawing a line down the center of this strip, moving steadily forward without lifting your instrument, something extraordinary occurs that seems to violate every instinct your mind has developed about the nature of surfaces and boundaries. You continue drawing, believing you are creating a line on one side of the paper, Yet somehow, without ever crossing an edge or reaching a boundary, your line eventually reconnects with itself on what should logically be the opposite side of the original surface. This is the essence of the Möbius strip, a surface with only one side, only one edge, and a topological property that renders the concepts of inside and outside, front and back, essentially meaningless within its structure. The psychological mechanism that makes this paradox so profoundly disorienting stems from our entire evolutionary history of navigating three-dimensional space filled with objects that possess two distinct sides. We have spent our entire lives understanding that surfaces have a front and a back, that edges mark clear boundaries between regions, that you cannot traverse from one side of a sheet to the other without crossing an edge or lifting your hand. The Möbius strip systematically violates each of these expectations. Our brains, which have become expert at predicting spatial relationships through countless experiences with conventional objects, suddenly encounter something that remains perfectly logical and mathematically valid, yet completely contradicts our intuitive understanding of how surfaces should function. What makes this paradox persist so powerfully in human consciousness is that we continue to encounter it even after we understand it intellectually. Knowing precisely how the Möbius strip is constructed, understanding the mathematical explanation for why it possesses only one surface, does nothing to diminish the visceral sense of wrongness when we experience it directly. We can construct one with our own hands, trace it with our fingers, yet the experience remains uncanny and somehow unsettling. Imagine a surface that exists in a state of continuous contradiction, a mathematical form that seems to fold through itself in ways that should be impossible in the three-dimensional space we inhabit, yet which mathematicians have proven can exist in four-dimensional space. And as we contemplate this form, we begin to understand that our perception of what is possible, and what is merely forbidden by the constraints of our dimensional prison, becomes fundamentally uncertain. The Klein Bottle is a surface with no inside and no outside, a topology so strange that if you were to travel along its surface, moving forward in what appears to be a single direction, you would eventually arrive back at your starting point, but inverted, as though the universe had turned you inside out while you were not paying attention. Unlike a sphere, which has a clear distinction between its interior and exterior, or a torus, which maintains a hole through its center, the Klein Bottle exists as a unified, continuous surface that somehow manages to pass through itself without ever actually intersecting. A feat that seems to mock the very foundations of three-dimensional geometry while remaining mathematically pristine and logically sound. The mechanism that allows this impossible form to exist relies on the hidden dimensions we cannot perceive, the fourth spatial dimension that our brains are not equipped to visualize or navigate, yet which mathematicians can describe with absolute precision using coordinate systems and topological equations. When we observe a Klein Bottle represented in three dimensions, what we see is necessarily a distorted projection, a shadow of the true form, much like how a two-dimensional drawing of a cube never truly captures the experience of a three-dimensional object, and what appears to be a self-intersection, a point where the surface impossibly passes through itself, is actually a passage through the fourth dimension that we lack the sensory apparatus to directly witness. The Klein Bottle demonstrates that our intuitive understanding of space, our confidence in the separation between inside and outside, our certainty about what surfaces can and cannot do, is entirely dependent on the number of dimensions we are able to move through and perceive. Imagine yourself standing at the base of a staircase that seems to ascend endlessly upward, each step climbing higher and higher into space, and yet when you follow the structure with your eyes from beginning to end, you somehow arrive back at the same point where you started, as though the entire construction has looped back upon itself in a way that should be physically impossible. This is the Penrose Stairs, a geometric impossibility first conceived by the mathematician Roger Penrose and his father Lionel Penrose in 1958, a figure that has since captivated artists, designers, and philosophers with its profound violation of our spatial intuitions. The staircase appears to be drawn in perfect perspective, with each step rendered in clean lines and careful shading, the railings extending predictably along the sides, the angles and proportions all seeming to obey the rules of three-dimensional space. Yet when you trace your finger along the path, moving from step to step, ascending what appears to be a continuous journey upward, you discover that you have mysteriously returned to your starting position without ever descending, without ever reversing direction, as though gravity itself has become confused about which way is actually up. The mechanism behind this paradox lies in how our brains process two-dimensional representations of three-dimensional space. Our visual system has evolved to interpret perspective cues with remarkable efficiency, reading depth from the angle of lines, the overlap of shapes, and the relative sizes of objects as they recede into the distance. The Penrose Stairs exploit these shortcuts ruthlessly by providing conflicting depth information in different regions of the figure, placing local perspective cues that are individually convincing but globally incompatible with one another. When you look at any single corner of the staircase in isolation, the perspective appears entirely sound, the depth seems clear and unambiguous. Your brain readily interprets it as a three-dimensional object. However, as your attention moves around the figure, following the path from corner to corner, the local contradictions accumulate without your conscious awareness, creating an impossible object that nonetheless feels visually coherent at every moment you examine it. What makes the Penrose Stairs particularly disorienting is that this contradiction is not a failure of the drawing itself, but rather an inherent feature of how we construct meaning from visual information. Imagine a three-dimensional object rendered in two dimensions, a triangle constructed with three corners that ought to be impossible, yet your eye follows the lines with complete conviction as they trace along clean, straight edges that seem to belong to a solid structure suspended in space. The Penrose Triangle, also known as the tribar, presents itself as a deceptively simple construction where three rectangular beams meet at right angles to form the vertices of a triangle. And when you first encounter it, your visual system immediately accepts it as a coherent representation of something real, something tangible, something that could theoretically exist if only the laws of three-dimensional geometry were slightly more forgiving. Each corner appears to sit perpendicular to the next, the lines are drawn with mathematical precision, and the shading subtly suggests depth and volume as though you were looking at an actual impossible object photographed from just the right angle. Your brain processes this image with remarkable speed and efficiency, performing the automatic calculations that have served human perception for millions of years, calculations that typically allow us to navigate physical space with confidence and accuracy. And yet in this case, those very same neural processes deliver you into a state of cognitive confusion, a gentle but persistent dissonance between what you are seeing and what you understand to be geometrically possible. The mechanism underlying this paradox operates at the intersection of two-dimensional representation and three-dimensional interpretation, for your visual system must necessarily translate flat images into spatial understanding, and it does this by relying on learned cues about perspective, shading, line convergence, and the relative positioning of objects within a frame. The Penrose Triangle exploits these deeply ingrained processing patterns by presenting visual information that is internally consistent at the local level but globally impossible, meaning that if you focus on any single corner or any individual edge, everything appears perfectly reasonable and three-dimensionally coherent. Yet the moment you attempt to trace your attention around the entire figure and synthesize all the spatial information into a unified whole, the contradiction becomes apparent and impossible to ignore. Imagine two geometric shapes constructed from identical colored pieces arranged on a grid, where the first configuration appears to contain a certain area, and the second configuration, using those exact same pieces rearranged, seems to contain a noticeably smaller area, as if a square unit has mysteriously vanished from the composition without any material leaving the system. This is the missing square puzzle, one of the most elegant demonstrations of how our visual perception and intuitive understanding of geometry can be systematically deceived by subtle mathematical sleight of hand that operates beneath our conscious awareness. The puzzle typically presents you with a right triangle divided into several smaller geometric pieces, including smaller triangles and rectangles, and when you rearrange these pieces into what appears to be the same triangle, a small square hole emerges in the interior of the shape, a gap that should not exist if the pieces truly constitute the whole. The mechanism underlying this illusion resides in a property so minute that human eyes cannot readily detect it without careful measurement and mathematical analysis. Specifically, that the hypotenuse of the original triangle is not actually a straight line, but rather a subtly bent line that contains a minuscule curve. A deviation so gradual and gentle that your visual system accepts it as perfectly straight, because your brain has been conditioned to interpret continuous edges as linear unless they show dramatic departure from straightness. The pieces, when you examine them mathematically, are constructed such that their slopes differ slightly from one another, meaning that when you rearrange the components into the second configuration, the supposed hypotenuse bends in the opposite direction, and this infinitesimal shift in curvature, this microscopic alteration in the trajectory of the boundary line, accounts for the mysterious vanishing square that appears to violate the conservation of area. What makes this paradox particularly fascinating is that it persists in deceiving observers even after they understand the mechanism, because the deviation in the hypotenuse remains so extraordinarily subtle that even knowing the explanation does not prevent your visual system from accepting the line as straight. And this gap between intellectual knowledge and perceptual experience reveals something profound about how our brains construct reality from sensory information rather than deriving it from pure geometric principles. Imagine standing on a beach with a map of your country's coastline, and you decide to measure its total length by carefully tracing every inlet, every bay, every small peninsula with your finger. You record a number. Now imagine doing the same thing with a more detailed map, one that shows smaller geographical features, and you measure again. The coastline is suddenly longer. Then you acquire an even more precise satellite image and measure once more, and the coastline grows longer still. You could continue this process indefinitely, obtaining increasingly detailed maps at smaller and smaller scales, and each time you measure, the coastline length increases. This is the Coastline Paradox, and it reveals something profound about the nature of measurement itself and how our attempts to quantify the natural world often collapse under their own logical weight. The fundamental mechanism at work here is one of scale dependency and the infinite complexity of natural boundaries. Coastlines are not smooth, mathematically simple curves that can be measured like a straight line on a piece of paper. Instead, they are fractal-like structures, possessing detail at every level of magnification. When you measure with a ruler that is 1 kilometer long, you skip over small bays and peninsulas that are smaller than your ruler. But when you switch to a ruler that is 100 meters long, you can now measure into those features, adding length to your total. As you continue to zoom in with smaller and smaller measuring instruments, you discover coves within coves, rocks creating tiny inlets, and irregular surfaces that seem to multiply endlessly. Each iteration reveals previously unmeasured complexity, and theoretically, as you approach infinitesimal scales, the measured length approaches infinity. This paradox emerged formally in the mid-20th century when mathematicians began investigating the properties of coastlines and realized that the answer to the seemingly simple question of how long a coastline is depends entirely on the scale at which you choose to measure it. There is no single, objective answer to this question, only a series of answers that vary according to the precision of your measurement tools. What makes this paradox so psychologically compelling is that we have developed a profound intuition that geographical features have fixed, definable properties. We believe that a coastline has a length, that a country has a specific area, that these are objective facts about the world that exist independent of how we measure them. Yet the coastline paradox demonstrates that this intuition is misleading. Imagine a grand hotel of impossible proportions, a structure that exists only in the minds of mathematicians and those who have ventured into the deeper territories of abstract thought, where the usual rules of space and accommodation dissolve into something far stranger and more unsettling. This is Hilbert's Infinite Hotel, a thought experiment conceived by the mathematician David Hilbert in the early 20th century, and it presents a scenario so counterintuitive that it fundamentally challenges our understanding of infinity, capacity, and the nature of fullness itself. In this hotel, there are infinitely many rooms, numbered 1, 2, 3, and continuing forever without end, stretching down corridors that have no terminus and across wings that extend into an incomprehensible distance. One evening, when every single room in this infinite establishment is completely occupied, when there is literally no empty space remaining because infinity has been filled to its absolute limit, a weary traveler arrives at the front desk seeking shelter for the night. The night manager, unflustered and professional, informs the guest that this presents no problem whatsoever and assigns them a room, which seems impossible until you understand the mechanism of the solution. The manager simply requests that every existing guest move to the next room, so the occupant of room 1 relocates to room 2, the occupant of room 2 moves to room 3, and this shifting continues infinitely down the line, leaving room 1 vacant for the new arrival. What makes this paradox so deeply disorienting is that we have somehow created space where none existed. We have accommodated an additional person into a structure that was already completely full, and yet logically, nothing has been destroyed or removed. This mechanism reveals something fundamental about infinity that our everyday experience cannot prepare us for. Infinity plus one is still infinity, and a completely full infinite structure can still accept more guests. The psychological mechanism operating here involves our intuitive understanding of capacity, which develops from living in a finite world where hotels have finite rooms and rooms that are occupied cannot simultaneously be empty. Our minds have evolved to understand fullness as an absolute state, a binary condition where something is either full or it is not, and this binary model fails catastrophically when confronted with infinity. Imagine a sphere, perfect and smooth, the kind you might hold in your hand or see floating in space, utterly simple in its geometry and utterly familiar in its form. Now imagine taking that sphere and beginning to grow horns from its surface, thin protrusions that extend outward like branches on a tree, and then imagine those branches themselves sprouting smaller branches, and those smaller branches sprouting even tinier ones, continuing infinitely inward and outward in a recursive pattern of increasing complexity. This is Alexander's horned sphere, a mathematical construct discovered by James Waddell Alexander in 1924, and it represents one of the most profound contradictions in topology, the branch of mathematics concerned with properties that remain unchanged through continuous deformation. The horned sphere begins as a simple enough concept, a topological space that is homeomorphic to a standard sphere, meaning it has all the essential properties of a sphere from a topological perspective, and yet it behaves in ways that seem to violate our deepest intuitions about what a sphere should do and how space should behave around it. What makes Alexander's horned sphere genuinely unsettling is the phenomenon known as wild embedding, the fact that while the sphere itself remains topologically equivalent to an ordinary sphere, the way it sits in three-dimensional space is so convoluted and infinitely intricate that it creates a boundary between two regions of space that cannot be separated by any continuous deformation without tearing the sphere apart. The complement of Alexander's horned sphere, the space that surrounds it and exists outside of it, is not simply connected, meaning that a loop drawn in this outer space cannot always be continuously shrunk to a single point without intersecting the sphere itself, a property that violates the Jordan curve theorem in its intuitive sense. This happens because the infinite branching structure of the horns creates a kind of topological barrier, a labyrinth so intricate that paths through space become trapped and tangled in ways that seem to defy the basic rules of three-dimensional geometry. Imagine a sphere, perfectly smooth and symmetrical, existing in the three-dimensional space around you, and now imagine that you have been tasked with the impossible. You must turn it inside out without tearing, cutting, or creating any creases in its surface, moving it through itself in a continuous motion until what was once the exterior becomes the interior and what was once hidden becomes exposed to the world. This is sphere aversion, a concept that defies our intuition so profoundly that mathematicians spent decades insisting it was absolutely impossible before Bernard Morin discovered in 1958 that it could actually be done, that a sphere could indeed be inverted through itself in a graceful, continuous transformation that requires no breaking of the material itself. When you first encounter this idea, your mind immediately protests, for everything in your physical experience suggests that turning something inside out requires either a seam or a tear, a deliberate opening through which the interior can escape and become exterior, yet the mathematical reality exists in a space slightly more complex than our everyday perception allows, a space where the sphere can twist and fold through itself in ways that seem to violate the rules we have come to trust absolutely. The process itself, when visualized through careful mathematical models and computer simulations, reveals stages that appear almost choreographed, moments where the sphere develops bulges and indentations, where parts of it pass through themselves in configurations that would be impossible if the sphere were made of actual rubber or fabric, yet in the realm of pure geometric transformation. Governed only by the principle of continuity and the allowance for self-intersection in four-dimensional space projected into our three-dimensional understanding, it becomes not just possible, but inevitable. What makes sphere aversion so psychologically disturbing is that it represents a fundamental challenge to our spatial reasoning, to our deep-seated belief that inside and outside are separate categories that cannot be reconciled through any smooth transformation. Yet the mathematics proves without question that they can be, that the distinction between interior and exterior is less absolute than we have always assumed, that our intuition about the nature of surfaces and boundaries is incomplete. Imagine a perfect cube, solid and immovable, sitting before you in three-dimensional space, and then imagine a second cube, identical in every way, passing completely through it as though the first cube were made of nothing but air and shadow. This is the essential paradox at the heart of Prince Rupert's cube, a geometric impossibility that has fascinated mathematicians and philosophers for centuries, named after Prince Rupert of the Rhine, who first posed the problem in the 17th century. The principle states that a cube can be passed through a hole cut into another cube of the same size, which violates our most fundamental intuitions about solids and space and the immutable nature of physical objects that occupy three dimensions. When we first encounter this concept, our minds rebel against it, because everything in our lived experience tells us that two objects of equal size cannot occupy the same space simultaneously, and yet the mathematics proves beyond any doubt that this passage is possible, that a cube can indeed thread through a carefully calculated opening without touching the edges of that opening at all, leaving the first cube structurally intact and whole. The mechanism behind this paradox relies on understanding how we perceive volume and dimension and the way that three-dimensional objects can be oriented in space in ways that seem to defy the logic of size. When we place a cube in its standard orientation, with edges aligned to cardinal directions, we perceive it as occupying a certain cubic volume. However, if we rotate that cube diagonally through space, tilting it along its body diagonal, the projection of that cube changes dramatically, becoming slimmer and more elongated, occupying less width in certain planes. The hole required to pass another cube through must be cut along this diagonal axis, creating an opening that seems impossibly small relative to the cube's actual volume. Yet through this narrow passage, the entire second cube can pass, threading through with mathematical precision. The opening, when examined closely, forms a shape that resembles a hexagon or a squared-off diamond, with proportions that seem far too meager to accommodate such a large object, and yet the geometry of space and rotation makes it inevitable that the passage occurs. We persist in finding this paradox remarkable despite having understood its mechanisms thoroughly, perhaps because our spatial intuition developed in an environment where such rotations and passages are rare, where our brains rarely need to calculate the projection of a cube rotating along its diagonal through three-dimensional space. Imagine you are standing at the edge of a coastline on a winter morning, observing the intricate patterns of frost that have formed along the boundary where land meets water, and you begin to notice something peculiar about the way the frozen crystals arrange themselves in an endlessly repeating geometric dance. The Koch Snowflake emerges from a deceptively simple instruction that seems to contradict the very nature of physical space itself. You start with an equilateral triangle, a perfect bounded shape with finite area and a measurable perimeter. Then on each side of this triangle, you locate the middle third of that line, and instead of letting it remain straight, you construct a small equilateral triangle pointing outward, creating a six-pointed star. You remove the base of this tiny triangle you just drew, leaving only the outward-pointing bump. Now repeat this process on every single line segment you have created, forever and ever, infinitely many times, each iteration adding more bumps, more details, more complexity to the boundary. What emerges is a shape with a perimeter that grows without limit, approaching infinity as you continue the process indefinitely, yet the area enclosed by this infinitely lengthy boundary remains finite and bounded, never exceeding a specific mathematical limit. This paradox challenges our intuitive understanding of how shapes behave, for we assume that a longer boundary should enclose a larger area, that as one measurement grows, the other should follow proportionally. The Koch snowflake violates this assumption completely and fundamentally. The psychological mechanism that allows us to comprehend this apparent impossibility involves recognizing that our everyday experience operates at scales where infinity remains abstract and theoretical. We have never actually encountered an infinitely detailed boundary in the natural world, though coastlines, mountains, and clouds approximate this fractal quality remarkably well. Our minds struggle to process the concept of endless complexity contained within finite space because we evolved in a world where such things do not exist at observable scales. We normalize this paradox by accepting it as mathematical truth, an artifact of abstract reasoning rather than physical reality, and we relegate it to the domain of pure mathematics where such counterintuitive properties are permitted to flourish. Imagine a cube sitting before you in perfect geometric form, solid and complete in every dimension, and then imagine dividing that cube into 27 smaller cubes arranged in a 3 by 3 by 3 grid, much like a Rubik's cube might be sectioned if you were to peer into its internal structure. Now remove the very center cube and the 6 cubes directly adjacent to it through their faces, leaving you with 20 smaller cubes arranged around the hollow void you have created in the middle. This process, which seems straightforward enough, becomes the foundation for a construction that defies intuition and challenges our fundamental understanding of dimension itself. Take each of those remaining 20 smaller cubes and repeat the exact same process, removing their centers and their face-adjacent neighbors, creating 20 smaller cavities within each of the 20 cubes, which means you now have 400 cubes, each one a perfect replica of the shape you began with, only smaller. Continue this process infinitely, repeating the same removal pattern at every scale, at every level of magnification, forever and ever into depths that mathematics allows but reality cannot quite reach. And you begin to approach the theoretical construction known as the Menger Sponge, a three-dimensional object that becomes increasingly hollow as you examine it more closely. The psychological paradox that emerges from contemplating this shape arises from a fundamental contradiction between two intuitive properties that we believe must coexist in physical objects. On one hand, as you remove more and more material through each iteration of this process, the object contains less and less actual substance, less and less volume, approaching zero volume as infinity approaches, which means that theoretically the completed Menger sponge would have essentially no volume whatsoever, no actual material content despite occupying space in 3 dimensions. Yet simultaneously, because the surface area of the sponge increases with each iteration, the boundary of this object becomes infinitely complex and infinitely expansive, covered with holes within holes within holes at every possible scale, creating a surface that never truly ends and can never be fully traversed or measured in any practical sense. Imagine you are looking at a simple equilateral triangle, the most fundamental shape in geometry, a form so basic that children learn to recognize it before they can read, and yet within this ordinary triangle exists a process of infinite subtraction that somehow creates something simultaneously empty and complete. You begin with a solid triangle, and then you remove the central triangle formed by connecting the midpoints of each side, leaving 3 smaller triangles in the corners, and then you repeat this process infinitely, removing the central triangle from each remaining triangle, and then again from each of those, continuing without end into scales so small that the human eye cannot perceive them. And what emerges is the Sierpiński Triangle, a shape that appears riddled with holes. A triangle that is somehow still a triangle despite being almost entirely hollow. A geometric figure that possesses the paradoxical quality of having a finite area yet an infinite perimeter. The psychological mechanism that makes this shape so profoundly disorienting is that it violates our intuitive understanding of what it means for something to exist. Because as you watch the process unfold in your mind, removing piece after piece, hole after hole, you begin to question whether anything substantial remains at all. And yet mathematically the triangle persists, still defined, still measurable, still present in a way that our conventional sense of presence cannot quite accommodate. We have normalized this paradox by placing it firmly within the abstract realm of mathematics, by declaring it a fractal, and thereby giving ourselves permission to stop questioning how shape can be simultaneously complete and infinitely perforated, how a boundary can be infinitely jagged while enclosing a finite space, and we rarely stop to consider that this shape represents something fundamental about the nature of existence itself, that complexity can emerge from simple repetitive rules, that absence and presence are not always opposites, and that the most essential truths about reality often appear to us first as impossibilities that we must learn to accept through the sheer mathematical weight of their own internal consistency. The Sierpiński Triangle appears in nature with startling frequency, in the branching patterns of trees, in the structure of sponges, in the distribution of galaxies across the cosmos, suggesting that the universe itself may be fundamentally drawn toward these patterns of recursive self-similarity, as if reality at every scale is engaged in the same ancient process of creating complexity through subtraction, presence through absence. Imagine you are standing at one end of a hallway and you wish to walk to the opposite wall. Before you can reach that wall, you must first travel half the distance to it, and this seems obvious and necessary. But then, once you have covered that first half, you are faced with a new distance remaining, and before you can cover that remaining distance, you must first traverse half of it, and then half of what remains after that, and then half again, infinitely subdividing the space that lies before you into smaller and smaller segments that must each be crossed in sequence. This is the dichotomy paradox, attributed to the ancient Greek philosopher Zeno of Elea, and it presents a logical problem that has troubled mathematicians and philosophers for more than 2,000 years. The paradox suggests that motion itself might be impossible, because in order to move from point A to point B, you would need to complete an infinite number of smaller movements, and completing an infinite number of anything seems, on its surface, impossible within any finite amount of time. The psychological mechanism at work here involves our intuitive difficulty with infinity and our tendency to treat infinite processes as though they operate under the same rules as finite ones. Our brains evolved to handle discrete, countable objects and events, not the abstract concept of infinite divisibility. And so when we contemplate crossing a room by first going halfway, then halfway again forever, our intuition rebels against the idea that this could ever be completed. We sense a logical trap closing around us, a mathematical snare that proves motion cannot exist, yet we observe motion happening constantly around us and within us every moment of every day. The resolution to Zeno's dichotomy comes from the mathematics of infinite series, specifically the concept that an infinite sum of terms can converge to a finite value when each successive term becomes progressively smaller. Each segment of distance that you must travel is half the previous one, and when you add all these infinite segments together, the total distance remains finite and achievable. Yet despite this mathematical resolution being well understood for centuries, the paradox persists in our collective consciousness as something genuinely puzzling, something that nags at our sense of how reality should work, because mathematics has resolved it in a way that our intuition still struggles to fully accept. Imagine a foot race between two competitors, Achilles, the legendary Greek warrior renowned for his speed and athletic prowess, and a tortoise, one of the slowest creatures to ever traverse the earth. The tortoise is given a head start, perhaps 100 meters ahead on an open track, while Achilles stands at the starting line, ready to pursue with all the velocity his powerful legs can generate. This seems like the most obvious and inevitable outcome in the history of competitions, a race that should be finished almost before it begins, and yet the ancient Greek mathematician Zeno of Elea constructed a logical argument suggesting that Achilles could never actually catch the tortoise, no matter how fast he ran or how slow the tortoise moved. The paradox unfolds through a series of seemingly reasonable steps. Before Achilles can catch the tortoise, he must first close the gap that initially separates them, so he must run to the point where the tortoise started. But during the time it takes Achilles to cover that distance, the tortoise has moved forward some amount, creating a new gap between them. Achilles must then close this new gap by running to where the tortoise now is, but again, during that interval of time, the tortoise continues moving forward, establishing yet another gap. This process continues infinitely, creating an infinite sequence of increasingly smaller distances that Achilles must traverse. Since Achilles would theoretically need to complete an infinite number of tasks before catching the tortoise, the argument suggests he would require an infinite amount of time, making it logically impossible for him to ever overtake his slower opponent. The psychological mechanism underlying this paradox operates through our intuitive struggle with infinity and our tendency to conflate the infinite divisibility of space with the infinite amount of time required to traverse it. When we examine the logical structure of the argument, it appears airtight and reasonable, which creates a cognitive tension between what our everyday experience tells us is obviously true and what the mathematical reasoning seems to prove is impossible. Our minds become trapped in a recursive loop, repeatedly accepting each step of the argument while simultaneously recognizing that the conclusion contradicts observable reality. The paradox persists in our consciousness because it highlights a genuine conceptual gap between how we understand motion intuitively and how mathematics describes it formally. Imagine stepping into a room where the basic proportions of space itself seem to have betrayed you, where a person standing in one corner appears to be a giant while their companion in another corner shrinks to the size of a child, and yet when they walk across the space, their size remains inexplicably constant, defying everything your eyes are telling you about the geometry before you. This is the Ames Room, a masterwork of architectural deception created by Adelbert Ames Jr. in 1935, a construction that demonstrates with elegant cruelty how profoundly our brains depend on unconscious assumptions about the world to make sense of what we perceive. The room itself is not actually a room at all in the conventional sense, but rather a deliberately distorted construction where the floor slopes at an angle, the walls converge unnaturally toward the back, the ceiling tilts in ways that contradict our expectations, and the windows are positioned and scaled to reinforce false depth cues to the observing eye. What makes the Ames Room so psychologically powerful is that it exploits a fundamental shortcut our visual system has evolved to take, namely the assumption that rooms are rectangular, that floors are level, that walls are parallel, and that light enters from above in predictable ways, assumptions so deeply embedded in our perceptual machinery that we rarely question them or even notice we are making them at all. When you look into an Ames room, your brain receives conflicting information between the shapes and sizes of objects within the space and the architectural cues that suggest distance and proportion. And rather than entertaining the possibility that the room itself is grotesquely distorted, your mind chooses to believe the simpler explanation, that one person is genuinely much larger than another, or that they are standing at vastly different distances away, and this happens automatically, without your conscious permission or awareness. The mechanism at work here is called size constancy, the perceptual system that allows us to recognize that an object remains the same size even when it appears smaller on our retina because it is farther away. But in the Ames room, this system catastrophically misfires because the room's distortion precisely cancels out the distance cues that would normally allow size constancy to work correctly. Imagine holding in your hands a simple three-pronged fork, a trident rendered in clean lines and careful perspective, drawn or carved in such a way that it appears to exist in three-dimensional space. Now examine it closely, beginning at the handle and moving your eye upward toward the three prongs that extend outward. The handle seems substantial and real, grounded in a way that makes logical sense, yet as your vision travels along the wooden shaft toward where the prongs should begin, something deeply unsettling occurs within your perception. The three distinct prongs appear to emerge from the handle, each one rendered with shadows and depth that convince your eye they exist in physical space, and yet when you trace the lines of the handle itself, you discover that it contains only two edges, not three. The handle is fundamentally incomplete, lacking the volume necessary to birth three separate prongs, and this impossible transition occurs without any clear line or boundary where the geometry breaks. Your mind experiences a kind of visual stutter, a moment where your brain attempts to reconcile the presence of three prongs with the physical impossibility of their origin point, and this reconciliation never fully completes itself no matter how long you stare. The mechanism that makes the impossible trident function as a paradox involves a carefully orchestrated violation of occlusion and continuity. When we view objects in three-dimensional space, our brains rely on consistent rules about what can hide what, how edges must connect, and how solid volumes must maintain their structural integrity across space. The impossible trident subverts these expectations by using ambiguous depth cues and strategic line placement to create two competing interpretations of the same image, and our visual system cannot adequately suppress either interpretation. The prongs read as existing in front of the handle in some areas, yet behind it in others, creating a topology that could never exist in physical reality. Despite decades of analysis and countless exposures to this paradox, we have not successfully trained our visual system to stop being fooled, nor have we learned to perceive the image in a way that fully resolves the contradiction. The impossible trident persists in capturing our attention because it reveals something fundamental about how our brains construct reality from incomplete sensory information, how we make assumptions about spatial relationships based on minimal evidence, and how these assumptions can be elegantly undermined through careful visual design. Imagine before you a simple line drawing of a cube, rendered in the most basic way possible, with 12 black lines arranged in that familiar three-dimensional configuration that we all recognize instantly as a cube floating in empty space. There are no shaded surfaces, no perspective tricks, no gradients or shadows to guide your eye toward any particular interpretation. It is merely the wireframe skeleton of a cube, what mathematicians and artists call an isometric projection, a perfectly valid way to represent three-dimensional space on a flat surface. You look at this image for a moment and it sits comfortably in your mind. The cube appears to recede into the distance in one direction, with one corner pointing toward you and the far corner pointing away. But then, without warning, without any change to the image itself, something shifts in your perception. The cube inverts, what was pointing toward you now points away, and what was distant suddenly feels close. The spatial arrangement has completely reversed, yet the lines remain exactly where they have always been, unchanging and motionless on the page before you. This phenomenon is the Necker cube, named after the Swiss naturalist Louis Albert Necker, who first described this visual illusion in 1832. And it represents one of the most elegant demonstrations of how our brains do not passively receive visual information, but rather actively construct it, constantly making assumptions and interpretations about the world we perceive. The mechanism underlying the Necker cube reveals something profound about how vision actually works within the human brain. When light enters your eyes and forms an image on your retina, the information that travels along the optic nerve to the visual cortex is fundamentally ambiguous. The two-dimensional projection of three-dimensional space contains insufficient information to determine absolute spatial relationships, and the brain must make educated guesses about depth, distance, and orientation based on experience and expectations. In the case of the Necker cube, the image provides no monocular depth cues like occlusion or perspective convergence, no binocular cues from stereoscopic vision, and no motion parallax to disambiguate which interpretation is correct. The brain therefore faces a situation where two completely different three-dimensional interpretations of the same two-dimensional image are equally valid from a purely mathematical standpoint. Imagine walking into a cafe and observing the tiled walls around you, perhaps a classic checkerboard pattern made of alternating light and dark squares arranged in perfect horizontal rows, with thin grout lines running between them in neat geometric precision. The pattern appears utterly regular and mathematically sound, yet as your eyes move across the surface, something peculiar emerges from the arrangement. The horizontal lines that should run perfectly parallel and level seem to tilt and undulate, creating the unmistakable impression that each successive row of tiles is offset or angled relative to its neighbors, as if the wall itself has developed a subtle wave-like distortion. This is the café wall illusion, discovered and documented in the pattern of tiles found in the wall of a London café in 1974. And it represents one of the most sophisticated demonstrations of how our visual system interprets contrast, alignment, and local spatial relationships at the expense of global geometric truth. The mechanism underlying this illusion involves the way our visual cortex processes boundaries and edges within the image, particularly how the visual system emphasizes the contrast between light and dark elements and interprets the relationships between adjacent shapes. When your eye encounters the alternating checkerboard pattern with its thin mortar lines, the local contrast between neighboring squares creates strong edge signals that your brain uses to infer three-dimensional structure and spatial organization. But these local edge detections become progressively misaligned as the pattern repeats, causing each row's horizontal axis to appear shifted relative to the one above or below it. The thin grout lines, rather than serving as absolute reference points for parallelism, actually amplify this effect because your visual system treats them as boundaries that define separate groups or segments, and the contrast relationships within each segment override the global information that all the lines are truly parallel. Imagine you have a napkin ring, that small cylindrical band of wood or metal or plastic that holds cloth napkins together at a dinner table, and you decide to drill a hole straight through its center, boring from one end to the other until you've created a hollow tunnel running the entire length of the ring. Now imagine you measure the height of the remaining material, the distance from the top of the ring to the bottom of the hole, and you discover that this height measures exactly 1 inch. The question then becomes, what is the volume of material remaining in that napkin ring after you've drilled through it? And here is where the paradox emerges with peculiar intensity. You might reasonably assume that the answer depends entirely on the original size of the napkin ring, that a large ring would leave behind more material than a small ring when you drill a 1-inch tall hole through each. Yet mathematics reveals something startling and counterintuitive. The volume of material remaining is determined solely by the height of what remains, not by any other dimension of the original ring. This means that every napkin ring in the world, regardless of whether it started as a slim, elegant band or a thick, generous cylinder, will contain exactly the same volume of material after drilling, provided the remaining height is identical. This result emerges from a beautiful symmetry in the mathematics of spheres and cylinders, where the formula for the remaining volume depends only on the height of the remaining material and produces what is called a napkin ring solid. The mechanism behind this paradox rests in how the geometry compensates itself across different dimensions. A larger original ring requires a wider hole to maintain the same remaining height, and these two factors, the initial size and the hole size, balance each other so precisely that they cancel out entirely from the final calculation. We accept this result intellectually once the mathematics is shown to us, yet it remains deeply unintuitive, because our spatial reasoning evolved to track objects we could hold and manipulate in our hands, not abstract geometric solids whose properties violate our expectations about how size should matter. The persistence of this paradox in mathematical literature and popular imagination speaks to how our minds compartmentalize formal knowledge and embodied intuition, allowing us to understand something completely while still feeling surprised by it each time we encounter it. Imagine holding in your hand a shape that appears to be a triangle, yet possesses a most unusual property that defies your immediate intuition about what triangles should be. This is the Reuleaux Triangle, a curve of constant width, discovered and refined by the 19th century German engineer Franz Reuleaux, though the concept had existed in various mathematical circles before his systematic examination of its properties. The shape is constructed by taking an equilateral triangle and then, using each vertex as a center point, drawing circular arcs that connect the other two vertices, creating three curved sides that bulge outward in a way that seems to violate our fundamental understanding of triangular geometry. When you measure the distance across this shape from any point on one curved edge to the opposite curved edge, you will find that this distance remains perfectly constant, regardless of the angle or direction from which you measure it, a property that circles possess, but that no triangle should ever possess according to classical Euclidean principles. The psychological mechanism that makes the Reuleaux triangle so profoundly disorienting stems from our deeply ingrained categorical expectations about shapes and their defining characteristics. We have learned throughout our lives that triangles are defined by having three straight sides and three vertices, and that circles are defined by their constant width and smooth curvature without corners. The Reuleaux triangle, however, occupies an impossible middle ground by combining the distinct visual identity of a triangle, complete with its three pronounced vertices and pointed corners, while simultaneously embodying the mathematical property of constant width that we exclusively associate with circles and spheres. This categorical confusion occurs because our brains have organized geometric knowledge into discrete boxes, and when a single object refuses to remain neatly within one box, it creates a kind of cognitive friction that feels unsettling and wrong. Additionally, the Reuleaux triangle challenges our assumption that shapes with the same width everywhere must be perfectly smooth and round, forcing us to reconcile the existence of a distinctly angular object that nonetheless maintains this supposedly circular characteristic throughout all its dimensions. What makes this paradox persist in our understanding is that the Reuleaux triangle occupies genuine utility in the real world, which normalizes its existence despite its conceptual strangeness. Imagine a wheel within a wheel, two perfect circles connected concentrically, rotating together as a single unit along a flat surface, and you will begin to understand the peculiar puzzle that has captivated mathematicians and philosophers for more than 2,000 years. Picture a large wheel with a diameter of 1 meter and nested within it, sharing the same axle and rotating in perfect synchronization, a smaller wheel with a diameter of half a meter. When the larger wheel completes one full rotation, traveling forward exactly 1 meter, because the circumference of a circle equals pi times its diameter, the smaller wheel must also complete one full rotation simultaneously because they are locked together on the same axis, yet the smaller wheel's circumference measures only half a meter. This creates an immediate logical contradiction, for the smaller wheel appears to have traveled the same distance as the larger wheel while possessing a smaller circumference, which violates everything we understand about how circles and rotations relate to linear distance. The mechanism underlying this apparent paradox involves a misunderstanding of what actually happens during the rotation, and when you examine the actual motion closely, you discover that the smaller wheel does not roll continuously across the ground like a wheel rolling freely would roll. Instead, the smaller wheel must slip and skip along the surface, or rather, it must have gaps in its contact with the ground, moments where it loses touch entirely and slides forward without rotating in relation to the surface beneath it. The smaller wheel's rotation is genuine, but its contribution to forward motion is supplemented by a skidding motion, creating a hybrid movement that is partly rotation and partly sliding. What makes this paradox so persistent and intriguing despite our modern understanding of mechanics is that it reveals something fundamental about how our intuitions fail when we confront coupled motion and shared axes of rotation. We have normalized the resolution by understanding that wheels in such configurations simply cannot both roll freely, and yet the paradox retains its power to unsettle us, to make us pause and reconsider what we actually mean when we speak of a wheel rolling, and to remind us that the natural world contains subtle complications hidden within the simplest mechanical systems imaginable. Imagine placing a coin flat on a table in front of you, and then imagine a second identical coin positioned directly beside it, touching along their edges. Now begin rolling the second coin around the perimeter of the first stationary coin, maintaining contact as it travels in a complete circle until it returns to its starting position. As you watch this coin rotate around its stationary twin, you might expect that the rolling coin completes exactly one full rotation during this journey, since it has traveled a distance equal to its own circumference. However, if you carefully observe the orientation of the rolling coin or mark its surface with a line or arrow, you will discover something deeply unsettling. The rolling coin has actually completed 2 full rotations by the time it returns to where it began. This discrepancy between our intuitive expectation and the mathematical reality reveals a fundamental gap in how our minds process rotational motion in space. The paradox emerges from the distinction between rotation and revolution, 2 forms of circular motion that our everyday experience has conditioned us to treat as interchangeable. When we calculate the distance traveled by the rolling coin, we measure the path of its center as it orbits around the stationary coin, and this orbital path itself constitutes a complete circle whose circumference equals the sum of both coin circumferences. This means the rolling coin does not travel merely its own circumference, but rather twice its circumference, resulting in 2 complete rotations rather than 1. Our minds struggle with this reality because we typically observe rolling coins in isolation or in linear paths, where we have learned to associate one circumference traveled with one rotation completed. The circular context fundamentally alters the geometry in ways that violate our accumulated intuitions about motion. We persist in expecting a single rotation because our brain uses a mental shortcut based on the stationary coin's circumference alone, ignoring the additional revolution around that coin's center point. This cognitive error feels particularly resilient because it challenges not just our intuition, but our entire framework for understanding how objects move through space. Even after understanding the mathematical explanation, watching a coin complete this rotation paradox still produces a sense of unease, as if the universe has quietly rearranged itself when we were not paying attention, leaving us with the unsettling realization that motion in circular contexts operates according to rules that remain somehow foreign to our deepest spatial understanding. Imagine you are climbing a staircase in a building you know well, perhaps in your own home or a familiar office, and as you ascend each step, you begin to count them carefully, one after another, step by step, moving upward with intention and focus. You reach what you believe to be the top of the staircase, the landing where you expect to arrive, and yet when you look around, you realize you have not actually climbed as many steps as you counted, or conversely, you have somehow climbed more steps than the staircase actually contains, creating a mathematical impossibility within the physical space you occupy. This is the essence of the staircase paradox, a phenomenon that emerges from the curious interaction between our counting mechanisms, our spatial perception, and the way our minds construct the experience of vertical movement through architectural space. The paradox typically manifests when we climb stairs while simultaneously engaging in other cognitive tasks, such as thinking about a conversation we had earlier or worrying about what awaits us at our destination, which causes our conscious counting to become desynchronized from our actual physical movements. Our brains are executing 2 parallel processes: the automatic, embodied process of climbing stairs and the deliberate, conscious process of enumeration, and these 2 processes operate at slightly different rates, creating a gap between the number we have counted and the number of steps we have actually traversed. The psychological mechanism underlying this paradox involves the concept of divided attention, wherein our cognitive resources are distributed across multiple simultaneous tasks, reducing the accuracy of our attention to either one individually. When we count steps while climbing, we allocate part of our mental resources to the counting task and part to the physical act of climbing, and this division creates small increments of desynchronization, moments where we skip a count or double count a single step, which accumulate across the entire ascent. Furthermore, our perception of steps can be influenced by the architecture itself, as the depth of the tread, the height of the riser, and the angle of ascent all affect how our body processes the motion, and sometimes our minds compensate for these variations in ways that distort our conscious count. The staircase paradox persists as a curious feature of human experience because we have largely normalized the disconnect between our automatic physical processes and our conscious awareness, accepting that our enumeration of everyday actions is often inaccurate without finding this particularly disturbing. Imagine yourself looking at a simple geometric triangle, drawn with precise lines on a piece of paper or displayed on a screen before you, and this triangle appears to be divided into 4 distinct regions, each region carefully marked with a different color or pattern so that you can easily distinguish one from another. And when you examine these 4 regions closely, you notice that 2 of them are larger shapes and 2 of them are smaller shapes, arranged in what seems like a logical and coherent composition within the overall triangular boundary. Now imagine that someone takes this same triangle, the exact same triangle with those same 4 regions, and rearranges those 4 regions into a different configuration, still keeping them all within the same overall triangular boundary, still maintaining the same outer shape and dimensions. And yet when you count the internal grid squares or measure the area using standard geometric principles, you discover with profound certainty that this newly arranged triangle contains more area than the original. As if material has somehow been created from nothing, as if the act of rearrangement has generated additional space where none previously existed. The mechanism that produces this impossible result operates through a subtle manipulation of what mathematicians call the slope differential, which is to say that the hypotenuse of the original triangle, that long diagonal line that forms the slanted side, does not actually maintain a perfectly consistent angle throughout its length, but instead exhibits a barely perceptible bend or curve that the human eye simply cannot detect at normal viewing distances, making the line appear straight when it is in fact microscopically curved. When the 4 internal regions are rearranged, this hidden curvature becomes more pronounced or shifts direction entirely, and the new configuration creates either a concave or convex edge along the hypotenuse where there was previously a different curvature, and this minute geometric shift translates into a measurable change in total area. Yet because the deviation from perfect straightness measures only millimeters across the entire length of a triangle that might span several inches, our visual perception, which evolved to detect large-scale threats and movements rather than infinitesimal geometric imprecisions, simply refuses to acknowledge that anything has changed at all. Imagine you are holding a chocolate bar in your hands, a perfectly ordinary rectangular confection divided into neat squares arranged in a grid pattern, perhaps 3 rows and 4 columns, making 12 individual pieces total. Now imagine that you carefully cut this chocolate bar in a very specific way, separating it into 2 portions along one of the internal divisions, and then you rearrange these pieces through a series of calculated shifts and slides, moving them across a table in a manner that seems geometrically sound, following what appears to be a logical spatial progression. When you push the final piece into place and examine your result, you discover something impossible has occurred. Your chocolate bar now contains 13 squares instead of the original 12, yet no chocolate was added and none was removed, and all the pieces still fit together into what appears to be a continuous, unbroken bar of chocolate. The paradox emerges from the subtle manipulation of proportions and angles within the rearrangement process, where thin slivers of additional area accumulate across the entire structure through cuts that are deliberately designed to obscure this redistribution, exploiting the limitations of human visual perception and our inability to precisely measure minute differences in angle and dimension when they are distributed across a complex reconfiguration. The mechanism functions because our brains are not naturally equipped to track infinitesimal changes in proportion across multiple simultaneous transformations, and we have become accustomed to trusting our eyes when geometric shapes appear to realign smoothly, assuming that if pieces fit together without gaps, then the total area must remain constant. An assumption that fails when the rearrangement is engineered specifically to violate this principle through imperceptible shifts in the angles of the cuts themselves. What makes this particular paradox so compelling and so persistent in human consciousness is that it represents a fundamental betrayal of one of our deepest spatial intuitions, the absolute conviction that matter cannot be created from nothing, that rearranging objects can change their configuration but never their total quantity. And yet here the visual evidence seems to contradict this immutable law, creating a cognitive dissonance that lingers even after we intellectually understand the deception, because our brains continue to send signals suggesting that more chocolate exists, even though we know rationally this cannot be true. Imagine a single continuous line drawn on a piece of paper, a line with no breaks or interruptions, moving smoothly from one point to another in an endless, winding path that somehow manages to pass through every single point in a two-dimensional square without lifting the pen even once. And as you trace this impossibly intricate path with your eyes, you begin to realize that what you are witnessing defies your fundamental understanding of what a line should be, and what a plane should be, and how these two basic geometric objects can possibly relate to one another. The space-filling curve, first rigorously constructed by the mathematician Giuseppe Peano in 1890, exists as a continuous function from a one-dimensional line segment into a two-dimensional square, meaning that somehow a single dimension can be stretched and folded and arranged in such a way that it occupies the entirety of two dimensions without ever breaking its continuity. And this revelation strikes at the very heart of our intuitive understanding of dimensionality and what it means for space to have a particular number of dimensions. What makes this concept so deeply unsettling is that our brains have evolved to think in terms of clear dimensional hierarchies, where a line is fundamentally thinner than a plane, where one dimension cannot possibly contain two dimensions, where the properties we associate with length cannot also encompass the properties we associate with area. And yet mathematics demonstrates through careful, irrefutable logic that a continuous curve can indeed visit every point within a two-dimensional region, essentially transforming a thin thread into a space-filling fabric through nothing but the cunning arrangement of its infinite convolutions. The mechanism behind this impossibility lies in the counterintuitive behavior of infinity itself. For while any finite approximation of a space-filling curve appears as a merely intricate wiggling path that covers some but not all of the plane, the infinite limit of this process reaches into every single point, becoming denser and more convoluted with each iteration, until the distinction between the curve itself and the area it traverses begins to blur into meaninglessness. Imagine taking a line segment, a simple line stretching from 0 to 1, and beginning a process of infinite subtraction that should theoretically leave you with nothing, yet somehow leaves you with something indefinable and strange. You start with your complete line, and you remove the middle third, the section between 1/3 and 2/3, leaving you with two smaller segments on either end. Then you take each of those remaining segments and remove their middle thirds as well, and then you do it again to each of the smaller pieces you create, and again, infinitely, forever removing middle sections from whatever remains. This process is called the Cantor Set, named after the mathematician Georg Cantor, who described it in the 1870s. And what emerges from this endless elimination is a mathematical object so paradoxical that it defies our intuitive understanding of what should exist and what should vanish. The psychological peculiarity here is profound because mathematically, you are removing so much material that the total length of all the segments you extract should equal the entire original line, and yet infinitely many individual points persist in what remains, creating a set that has zero total length but somehow contains uncountably infinite points. More points than there are natural numbers, which should be impossible in any rational framework. We have accepted this paradox into our formal mathematical systems by developing rigorous definitions of infinity and measure and dimensionality, allowing these contradictions to coexist peacefully within our theories, treating the Cantor set not as an error, but as a legitimate mathematical object that reveals how the very fabric of continuous space breaks down under infinite scrutiny. Despite the fact that the Cantor set should not exist according to our everyday understanding of geometry and substance, it remains not only accepted, but celebrated as one of the most elegant demonstrations that mathematics operates in realms where human intuition cannot follow, where something can be simultaneously empty and infinitely populated, nowhere and everywhere at once. The Cantor Set appears unexpectedly throughout nature and mathematics, in the distribution of galaxies across the universe, in the branching patterns of blood vessels, in the structure of coastlines, suggesting that this strange mathematical phantom is not merely an abstract curiosity, but a fundamental organizing principle of reality itself, a skeleton upon which the physical world hangs its infinite complexity. Imagine ascending a staircase that appears to climb continuously upward, step after step, each one taking you higher and higher into space. Yet somehow you arrive at exactly the same elevation where you began, neither higher nor lower than when you started your journey, a phenomenon that seems to violate the most fundamental laws of physics and geometry that govern our three-dimensional world. This is the Devil's Staircase, a mathematical construction that exists most famously in the Cantor function, a curve that rises from 0 to 1 while remaining perfectly flat across intervals that together comprise almost all of its length, creating the unsettling sensation that something is simultaneously climbing and not climbing at all. The Devil's Staircase emerges from a deceptively simple iterative process where you begin with a straight diagonal line from the bottom left to the top right, then repeatedly remove the middle third of each segment and replace it with a horizontal step that goes neither up nor down. Repeating this pattern infinitely across finer and finer scales until you construct an object that appears to climb smoothly, yet consists almost entirely of flat sections separated by infinitesimally small vertical jumps. What makes this construction so deeply paradoxical is that the total vertical distance traveled equals exactly the vertical distance between start and finish, yet the function manages to rise from 0 to 1 through an uncountably infinite collection of flat regions and infinitesimal steps, each contributing nothing measurable to the total height, yet somehow collectively achieving the complete ascent. The psychological disorientation this creates stems from our intuitive understanding that climbing must involve continuous motion upward. That height is accumulated gradually through sustained effort. Yet here we encounter a function that technically rises everywhere it rises at all, but rises so slowly and across such a fragmented pattern that it reveals the deep strangeness lurking within the concept of continuity itself. Imagine you are holding a single needle, a perfectly straight rod of finite length, and you find yourself in an empty plane with nothing but space stretching endlessly in all directions around you, and your task is deceptively simple. You must rotate this needle through a complete 360-degree turn so that it points in every possible direction, returning finally to its original orientation. But here is where the paradox begins to unfold in your mind. What is the minimum amount of space, the smallest possible area, that you would need to accomplish this rotation without lifting the needle from the plane or allowing it to pass through itself? Your intuition might whisper that you could simply spin the needle in place like a compass needle rotating above a single point, and the area required would be infinitesimally small, nearly approaching 0. Yet this intuition collides violently with a mathematical reality discovered by a Japanese mathematician named Soichi Kaikya in 1917. Through rigorous geometric construction, mathematicians have demonstrated that you can rotate a needle through a complete revolution while confining it to an area far smaller than the circle that would naturally contain it. And through increasingly clever arrangements of rotations and translations, mathematicians discovered something even more unsettling. The infimum, the greatest lower bound of possible areas, approaches 0 itself, suggesting that theoretically you could rotate a needle in an arbitrarily small space, a space so diminished that it seems to violate every intuitive principle of how objects move through geometry. The mechanism underlying this strange result lies in the interplay between continuous motion and the clever exploitation of geometric configuration, where the needle performs rapid, intricate maneuvers involving rotations combined with parallel translations that collectively require less and less bounded area as the patterns become increasingly refined and sophisticated, creating shapes like deltoids that appear to accomplish rotation within surprisingly compressed boundaries. Imagine running your fingers across the surface of a sphere, trying to comb all the hair lying flat in one single direction without creating any bumps or whorls or disruptions in the pattern, and you will immediately encounter an impossibility that mathematics has formalized into what we call the hairy ball theorem, a concept that haunts the boundary between pure abstraction and the physical world we inhabit. The theorem states with absolute certainty that it is impossible to comb the hair on a sphere completely smooth in every direction simultaneously, meaning there must always exist at least one point where the hair stands straight up perpendicular to the surface, creating what mathematicians call a singularity or a fixed point where the vector field cannot be continuously defined. This peculiar mathematical truth emerges from the topology of the sphere itself, a shape that possesses fundamental properties that resist our attempts at uniform organization. And when we consider this in 3 dimensions, the implications become genuinely unsettling because we are forced to contemplate how certain geometric constraints are not merely practical difficulties, but rather absolute impossibilities woven into the fabric of spatial structure. The psychological mechanism underlying our relationship with this theorem involves recognizing that our intuitions about smoothing and combing and creating uniform patterns across surfaces are fundamentally mistaken, that we have developed expectations shaped by working primarily with flat planes and simple shapes. And when we encounter the sphere, we discover that curvature introduces constraints that our spatial imagination never prepared us for. What persists despite logical analysis is our continued surprise at this result, our lingering feeling that surely with enough patience or ingenuity we could somehow violate this mathematical law, a resistance that reflects how deeply we resist accepting that certain problems have no solutions whatsoever, that some impossibilities are not failures of effort, but rather signatures of deeper truths about the geometry of space itself. And as you drift toward sleep contemplating this eternal combing problem, you might notice how the Earth itself with its wind patterns and weather systems demonstrates this theorem in action, with cyclones and anticyclones and circulation patterns that must always contain points of rotation, always creating vortices where the uniform flow breaks down into singularities that mathematics predicted long before we could observe them swirling in our atmosphere. Consider 3 rings of metal or rope arranged in 3-dimensional space in such a way that each ring passes through the other 2, creating an interlocked chain that appears inseparable and permanent, yet possesses a peculiar quality that defies our intuitive understanding of how objects should behave when interconnected. If you were to remove any single ring from this arrangement, the remaining 2 rings would fall apart completely and separate entirely, despite the fact that before the removal, all 3 rings appeared to be equally and fundamentally locked together in a symmetric relationship. This is the paradox of Borromean Rings, named after the Italian Borromeo family who featured this configuration in their coat of arms, a symbol they chose perhaps without fully grasping the philosophical implications of what they had selected to represent their lineage. The 3 rings demonstrate a form of interdependence that operates on a principle fundamentally different from what we experience in ordinary life, where if 2 objects are locked together, they remain locked together regardless of what else surrounds them. The psychological mechanism that makes Borromean rings so profoundly unsettling to contemplate rests in our deep-seated expectation that physical connection should be transitive, that if ring A holds ring B and ring B holds ring C, then ring A must somehow be holding ring C even if they do not directly touch. Yet this configuration violates that expectation completely, suggesting instead that interdependence can exist in a state where no pair of objects actually requires the third, and yet the third is absolutely essential for maintaining the whole. We have normalized this paradox by relegating it to the realm of mathematical curiosities and topological abstractions, treating it as an amusing footnote in the study of knot theory and 3-dimensional geometry, something interesting but ultimately irrelevant to the way the physical world actually functions around us. Yet this configuration exists not merely in theoretical space, but has been constructed countless times in metal and plastic and rope, proving that reality itself permits this seemingly impossible arrangement. And our normalization of the Borromean rings as mere mathematical oddities masks a deeper truth about how our assumptions regarding connection and dependency may themselves be insufficient when applied to certain configurations of space. Imagine a necklace made not of pearls or gold, but of infinitely many solid tori, each one linked through the next in an endless chain that somehow closes upon itself in a way that feels geometrically impossible when you truly grasp its implications. This is Antoine's necklace, a construction named after the French mathematician Louis Antoine, who first described it in 1920, a topological object so peculiar that it challenges our most basic intuitions about what it means for something to be connected, separated, or even to exist in 3-dimensional space at all. The necklace begins as a simple concept, Take a solid torus, that donut-shaped object with a hole through its center, and link another torus through that hole, then link a third through the second, and continue this process infinitely, each torus smaller than the last, shrinking down toward a limit point while maintaining the essential property that every single torus is physically and genuinely linked through its neighbors. What makes this construction so disturbing to contemplate is not merely that it extends infinitely, for infinity itself has become somewhat familiar to our minds through mathematical exposure, but rather that the complement of this necklace, that is, all the space that is not occupied by any of the tori, possesses a topological property so unusual that it seems to defy our expectations about how three-dimensional space should behave. When you examine what remains after removing Anton's necklace from ordinary three-dimensional space, you discover that this remaining space is not simply connected, meaning that there exist closed loops within it that cannot be continuously shrunk down to a single point without leaving the space itself. The psychological mechanism behind our difficulty in visualizing this phenomenon stems from our evolutionary adaptation to navigating at human scales, where we develop strong intuitions about solidity, separation, and the behavior of objects. Our brains are fundamentally calibrated to understand a world where things either touch or do not touch, where boundaries are clear, and where the relationship between an object and the space around it follows predictable rules. Yet Anton's necklace violates none of the mathematical rules that govern three-dimensional topology, while simultaneously producing outcomes that our spatial reasoning finds nearly impossible to internalize. Imagine standing at the edge of a landscape where three bodies of water meet, and despite your most careful observations, you cannot determine which water belongs to which lake, nor can you trace any clear boundary that separates one from the other. This is the paradox of the lakes of Wada, a topological phenomenon discovered in 1917 by the Japanese mathematician Kunizo Yoneyama, who constructed a mathematical proof so counterintuitive that it challenges our most fundamental assumptions about how space itself can be divided and organized. The lakes of water are three connected regions in a plane, and here lies the paradox: they share the exact same boundary. Every point on the border between any two of these lakes is simultaneously also a point on the border of the third lake, creating a situation where you cannot find any location that belongs exclusively to the boundary of just two lakes. This means that if you were to walk along what you believe to be the shoreline separating Lake A from Lake B, you would discover that at every single step, the boundary of Lake C is also touching your location, interweaving itself through the space in a way that seems geometrically impossible, yet mathematically irrefutable. The construction of such lakes requires an iterative process where the regions grow inward like a mathematical breathing, expanding and contracting in infinitely detailed patterns, creating a boundary so convoluted and intricate that it touches itself at an infinite density of points. What makes the lakes of Wada so psychologically disturbing is that it violates our intuitive understanding of separation and adjacency. Our minds evolved to navigate physical space where boundaries are relatively simple, where borders between territories are either present or absent, where things are clearly on one side or another. We expect that if something separates two regions, it should create a clear delineation, a distinct line where one thing ends and another begins. Yet the lakes of Wada demonstrate that topology permits configurations where this expectation collapses entirely, where the notion of being next to something becomes philosophically ambiguous. The mechanism underlying this paradox rests in the mathematical concept of dense sets and fractal-like boundaries that can be constructed through careful iterative procedures. Imagine standing in a landscape where the very ground beneath your feet curves away from you in all directions, not like the gentle dome of our familiar Earth, but inward, like the surface of an infinite saddle or the interior of a vast cosmic bowl turned upside down. And as you walk forward through this strange terrain, you notice something profoundly unsettling about the distances and angles that govern this space. In hyperbolic geometry, the parallel postulate that has anchored our understanding of Euclidean space for millennia simply ceases to exist. And instead of one unique line parallel to a given line through a point, there are infinitely many lines that never intersect with the original, spreading outward like the branches of an endlessly dividing tree, each one maintaining its perfect parallelism while occupying the same geometric neighborhood. The angles of a triangle drawn upon this curved surface sum to less than 180 degrees, a fact that feels like a violation of something fundamental about how shapes should behave. And when you measure the distance around a circle in this geometry, you discover that the circumference grows exponentially rather than proportionally with the radius, meaning that space itself seems to expand outward in a cascade of increasingly generous proportions. What makes hyperbolic geometry so conceptually disorienting is that it is not merely a mathematical abstraction divorced from reality, but rather a perfectly valid and internally consistent geometric system that actually manifests in the natural world, appearing in the curved surfaces of saddle-shaped molecules, in the large-scale structure of the universe itself, as suggested by modern cosmology, and in the fractal patterns of coral reefs and lettuce leaves that seem to fold impossibly upon themselves to maximize surface area. Our minds struggle to visualize this geometry because we have evolved in a world dominated by Euclidean space and spherical surfaces, and our brains have become exquisitely tuned to interpret sensory information through this particular lens. Yet hyperbolic space persists around us and within us despite this perceptual blindness, a geometric truth that operates beyond the boundaries of human intuition, reminding us that the universe is far more strangely configured than our everyday experience could ever suggest. Imagine standing in an infinitely long hallway with perfectly straight walls that never converge, never diverge, and never meet, stretching endlessly into both directions with absolute geometric precision. You're standing between two parallel lines, and your entire understanding of space depends on the assumption that these lines will remain forever separate, that no matter how far you walk forward or how vast the distance becomes, they will maintain their equidistant relationship to one another indefinitely. This principle seems so fundamentally obvious, so rooted in our everyday perception of reality, that it requires almost no conscious effort to accept it. The walls of your room are parallel to one another. The edges of your bed maintain their distance from each other. The rails of a staircase demonstrate this principle with such apparent clarity that we rarely question whether it could be any other way. Yet this geometric certainty, which Euclid himself codified as one of his 5 foundational postulates more than 2,000 years ago, is actually not a provable truth, but rather an assumption, an axiom chosen because it felt intuitively correct, rather than because it could be logically derived from more fundamental principles. For nearly 2 millennia, mathematicians attempted to prove this postulate from the other 4 axioms, believing that once they succeeded, they would have completed a perfect geometric foundation for all of mathematics. The psychological mechanism behind our acceptance of the parallel postulate lies in the limitations of human spatial perception, which evolved in a relatively flat, locally Euclidean environment where our eyes and bodies operate at scales where curved space appears straight. We cannot naturally perceive the gentle curvature of Earth's surface from ground level, nor can we intuitively grasp the warping of spacetime around massive objects, and so our brains construct a mental model of space as fundamentally flat and Euclidean. Every time you assume that railroad tracks remain the same distance apart, or that a perfectly straight road extends infinitely without deviation, you are unconsciously validating Euclid's postulate. However, in the 19th century, mathematicians discovered that the parallel postulate is not universally true, that in non-Euclidean geometries, parallel lines can either converge toward one another or diverge away from each other depending on whether the space itself is positively or negatively curved. A revelation that fundamentally shattered the notion that one geometry could describe all possible spaces. Imagine standing at the exact center of a vast circular arena, watching as an infinite landscape compresses itself into the finite space of that circle's boundary. And as you move toward that boundary, the geometry itself begins to warp and bend around you in ways that seem to defy the ordinary rules of space. The Poincaré Disk is a mathematical model of hyperbolic geometry, a non-Euclidean space where the familiar axioms of flat geometry no longer apply, where parallel lines diverge from one another, where triangles contain angles that sum to less than 180 degrees, and where the universe itself curves inward in a way that allows infinite distance to fit within a finite container. In this strange geometry, a being walking toward the boundary of the disk would experience increasingly strange distortions, their footsteps growing slower relative to an outside observer, the space around them expanding endlessly even as they remain visibly contained within the circle, creating a perfect illusion of infinite worlds compressed into a bounded region. The psychological mechanism at work here involves the clash between our intuitive understanding of space as flat and uniform and the mathematical reality that space can be curved, compressed, and reorganized according to different geometric rules, challenging our deepest assumptions about how distance and direction function in the universe. We have normalized this paradox through its application in fields ranging from cosmology to art, treating the Poincaré Disk not as a violation of reality, but as an alternative lens through which to understand it, a reminder that our perception of space is merely one possible interpretation among infinite others, and that the universe is far stranger than our everyday experience suggests, containing geometries that contain themselves in ways we can barely visualize, let alone fully comprehend. When we gaze at the intricate tessellations that fill the Poincaré disk, those hyperbolic tilings where identical shapes repeat infinitely toward the boundary, we glimpse a fractal self-similarity that mirrors the structure of the universe itself, suggesting that the infinite and the finite may be not opposites but different perspectives on the same underlying reality. Imagine you're standing on the surface of a globe, and you decide to draw a triangle using the shortest possible paths between 3 points, which we call geodesics or great circles. If you were to measure the 3 interior angles of this triangle on a flat map, they would add up to exactly 180 degrees, as we learned in our earliest geometry lessons, a truth that feels as immutable as gravity itself. But on the surface of a sphere, something extraordinary and deeply unsettling occurs. When you carefully measure those same 3 angles on the curved surface, their sum becomes something greater than 180 degrees, sometimes significantly greater, and this surplus is called the spherical excess. The amount of excess depends entirely on how large the triangle is relative to the sphere itself. A small triangle drawn on a basketball might have only a few extra degrees beyond 180, creating barely perceptible deviation from the rules we know. But consider a vast triangle on Earth's surface, with one vertex at the North Pole and 2 vertices on the equator separated by 90 degrees of longitude. Each angle at the equator measures 90 degrees, while the angle at the pole also measures 90 degrees, yielding a total of 270 degrees, an excess of 90 degrees that cannot be ignored or rationalized away through measurement error. This happens because space itself is curved, and the shortest paths between points on a sphere naturally bend with that curvature, forcing the angles of any triangle inscribed upon it to exceed the flat world total. What makes this phenomenon so psychologically disorienting is that it fundamentally challenges our intuitive understanding of geometry as something universal and unchanging. We have spent our entire lives trusting that the rules of triangles are absolute, that angles must sum to 180 degrees, that these principles transcend location and context. Yet spherical excess reveals that geometry itself is not absolute, but rather dependent upon the underlying space in which it exists, revealing that curved surfaces generate their own geometric laws that are perfectly consistent within their own domain, but utterly alien when compared to the flat assumptions of our childhood. Imagine you are holding a piece of paper, perfectly flat and smooth, and you decide to roll it into a cylinder without stretching or tearing it, simply curving it around itself in the most natural way possible, and when you have done this, you notice something peculiar. The distances between points on the paper remain exactly the same as they were before, the angles between lines are preserved, and yet the surface itself has fundamentally transformed into something that looks and feels entirely different from what it was moments ago. This is the essence of what Carl Friedrich Gauss discovered and called the Theorema Egregium, or the remarkable theorem, a principle so profoundly strange that it seems to suggest surfaces can change their shape while mysteriously maintaining their deepest geometric properties, a paradox that reveals something unsettling about the nature of space itself. The theorem states that the Gaussian curvature of a surface, which measures how bent or twisted it is at any given point, is an intrinsic property that cannot be altered by bending the surface without stretching or tearing it, meaning that when you roll your paper into a cylinder, the curvature intrinsic to the surface remains zero even though you have clearly bent it in 3-dimensional space. And this strange dichotomy emerges because there is a difference between how curved something appears when you view it from outside, and how curved it actually is when you experience it from within. The psychological weight of this discovery lies in the unsettling realization that our intuitions about shape and form are fundamentally unreliable, that 2 objects which appear radically different to our eyes and hands might nonetheless be mathematically identical in ways that matter deeply to the geometry living on their surfaces, and that the universe might contain transformations and equivalences that our ordinary perception simply cannot detect, leaving us perpetually uncertain about whether what we see is truly what is. We have learned to accept this strangeness as simply the way mathematics works, incorporating it into our understanding of differential geometry as though it were obvious all along. Yet the original insight remains profoundly disorienting when we truly contemplate it. That a cylinder and a flat sheet are, in a very real sense, the same thing, that curvature and flatness can coexist in the same object depending on your perspective, and that our three-dimensional universe might be playing similar tricks with space itself at scales we cannot perceive. Imagine yourself in a kitchen, holding a fresh orange in your hand, and you begin the familiar ritual of peeling away its thick, textured skin to reveal the fruit within. And as you separate that outer layer from the delicate white pith beneath, you notice something that most people never consciously acknowledge. The peel seems to take up remarkably little space relative to the whole fruit, yet when you finish peeling and look at the intact skin in your palm, it appears to occupy nearly as much volume as the fruit itself once did when it was whole. And this perceptual inconsistency creates a profound cognitive dissonance that we experience but rarely examine. The paradox emerges because our brain processes volume and surface area through fundamentally different visual and tactile channels, and when the orange is whole and spherical, our spatial judgment integrates the dense interior mass with the thin exterior boundary in a unified three-dimensional perception. But the moment that peel separates and flattens or crumples in your hand, the same brain that moments before estimated its negligible thickness now confronts what appears to be a substantial quantity of material, almost as if the act of removal has somehow generated additional matter. This occurs because peeling creates a dramatic transformation in how our visual cortex receives spatial information. The curved surface of an intact sphere presents continuous visual edges and shadows that our brain interprets as a thin shell, whereas a crumpled or flattened peel presents multiple surfaces, creases, and layers that catch light differently and create an impression of greater volume through increased visual complexity rather than actual increased mass. Furthermore, our proprioceptive feedback from handling the peel contributes to this illusion, as the thin skin feels surprisingly substantial when gathered in your hand, providing tactile confirmation of a false size estimate. And this multisensory convergence upon an incorrect conclusion demonstrates how our spatial reasoning relies not on accurate measurement, but on pattern recognition systems evolved for immediate survival rather than precision. And we have become so accustomed to this recurring domestic paradox that most people peel oranges without ever questioning why their intuition so consistently misestimates the relationship between the intact peel and the complete fruit, treating this moment of perceptual surprise as merely a curious quirk of attention rather than a fundamental vulnerability in how we construct our sense of three-dimensional space. Imagine standing in an airport terminal, looking at a flight map projected on the wall, and you notice something that seems almost wrong about it. A flight from New York to Tokyo appears to arc northward over Alaska and Russia rather than traveling in a straight line across the Pacific, and this peculiarity has puzzled travelers and cartographers for centuries, yet it represents one of the most fundamental truths about navigation on a sphere. When pilots and sailors plot the shortest distance between 2 points on Earth, they are not following what appears shortest on a flat map, but rather what is actually shortest when measured along the surface of a three-dimensional globe, and this path is called a great circle route, a concept so counterintuitive that it seems to violate our basic spatial reasoning. A great circle is any circle drawn on a sphere whose center is the center of the sphere itself, and the equator and all meridians of longitude are great circles, while most lines of latitude are not, and the shortest distance between any 2 points on a sphere always lies along a great circle, not along the straight line that would exist in flat space. When cartographers project the spherical Earth onto a flat map, something remarkable and disorienting happens. Distances become distorted, angles shift, and the paths that appear straight on paper are no longer the true shortest routes through physical space. And what looks like a detour across the Arctic becomes, in three-dimensional reality, the most efficient path for an aircraft to travel. The human mind, evolved in a landscape where distances and directions operated on relatively small, locally flat scales, struggles deeply with this concept, because our intuition about straightness developed in a two-dimensional or locally flat three-dimensional world, where we learn that the shortest distance between 2 points is always a straight line, a principle so ingrained that we accept it without question. Yet when you wrap that principle onto a sphere, straightness itself transforms into something that curves when viewed from outside, and what is geodesically straight on the surface appears as an arc when projected onto paper, creating a permanent cognitive dissonance that persists even after we intellectually understand the mathematics. Consider the moment you first truly looked at a map of the world, perhaps in a classroom or on a wall, and accepted without question that Greenland appeared roughly the same size as Africa, that North America seemed to dominate the upper portion of the globe, and that the polar regions stretched endlessly across the edges like frozen borders containing all other lands. This image has become so normalized in our collective consciousness that we rarely pause to examine what we are actually seeing, which is a fundamental distortion of reality so profound that it renders our planet almost unrecognizable. The Mercator projection, created in 1569 by Flemish cartographer Gerardus Mercator, was designed with a specific pragmatic purpose: to maintain accurate compass bearings for maritime navigation. Yet in solving one problem, it created a geographical lie so persistent that it has shaped centuries of geopolitical perception and continues to do so today. In truth, Greenland occupies approximately 2.1 million square kilometers of surface area, while Africa spans an astounding 30 million square kilometers, making the continent roughly 14 times larger than Greenland appears on a standard world map. The distortion grows more severe as you move toward the poles, a mathematical inevitability that occurs when projecting the curved surface of a three-dimensional sphere onto a flat two-dimensional plane. And yet we accept these warped representations as truth because they serve our navigational needs, and because the maps we see repeatedly confirm what the previous maps told us. Our brains internalize these projections through repeated exposure and education, creating mental models of planetary geography that bear increasingly distant relationships to actual physical reality. And this cognitive acceptance persists despite our intellectual awareness that maps must distort because geometry itself forbids perfect translation from sphere to plane. We continue to teach children with these projections, to reference them in media, to accept them as standard, and in doing so we have collectively agreed to a shared geographical fiction that influences how we perceive the relative importance and scale of different regions, all while forgetting that the very act of flattening the world necessarily betrays it, and no matter which projection we select. We are always choosing which truths to preserve and which to sacrifice to the impossible dream of perfect cartography. Imagine standing in a perfectly darkened room where a single source of light casts the shadow of a four-dimensional hypercube, or tesseract, onto a two-dimensional surface before you. And as you watch this shadow shift and rotate through impossible angles, you begin to notice that the shadow seems to contain information about dimensions you cannot directly perceive. Yet your mind insists on trying to reconstruct the three-dimensional object that must be casting it, even though no such object exists in your three-dimensional space. The Tesseract Shadow appears as a cube within a cube, connected by lines that seem to defy the rules of perspective you have learned throughout your entire life, with the inner cube appearing simultaneously smaller and more distant, yet also somehow nested within the outer structure in a way that suggests a relationship that cannot possibly exist in the spatial framework you inhabit. Your eyes follow the edges, counting them, finding 12 on the outer cube and 12 on the inner cube, connected by 8 diagonal lines, totaling 32 edges in a configuration that your brain recognizes as mathematically consistent even as it feels visually impossible. This occurs because your visual cortex is attempting to apply three-dimensional geometric logic to a two-dimensional projection of a four-dimensional object, a process that creates a profound cognitive dissonance between what you see and what you know should be possible. The mechanism at work here involves your brain's deeply ingrained assumption that all shadows cast by physical objects must represent a three-dimensional form in three-dimensional space, an assumption so fundamental to your perception that it continues to operate automatically even when you consciously understand that you are observing something that violates this principle entirely. Your neural pathways have evolved to extract meaningful spatial information from shadows, to reconstruct depth and form from flat images, and this adaptive mechanism becomes a liability when confronted with mathematical projections that have no physical analog in the world you perceive. What persists despite our understanding that this represents a projection of a four-dimensional object is an almost involuntary attempt to mentally rotate and interpret it as a three-dimensional form. and we have normalized this impossible task to the degree that we accept the Tesseract Shadow as merely a curious intellectual exercise rather than acknowledging it as evidence of the fundamental limitations built into our sensory apparatus and the geometry of our dimensional existence. Imagine laying out a piece of paper and drawing a cross shape made of 6 squares, then adding 2 more squares to opposite sides of that cross, creating a pattern that looks almost like a flattened flower or an intricate puzzle piece. And this is what we call the net of a hypercube, which is the 2-dimensional unfolding of a 4-dimensional cube that exists in a mathematical space we cannot directly perceive or visualize. When we look at this net drawn on our flat paper, we are essentially seeing instructions for how to fold a shape that cannot physically exist in our 3-dimensional world. Yet the mathematics is entirely real and consistent, as if the universe is showing us a blueprint for something that our eyes and hands could never actually construct or hold. The psychological tension emerges because our brains have evolved to understand objects in 3-dimensional space, and when we attempt to mentally fold this net into a 4-dimensional hypercube, we experience a kind of conceptual vertigo, a sensation of our spatial reasoning reaching a boundary it cannot cross, as our minds try desperately to rotate and stack these squares in ways that would require moving through a dimension we have no sensory experience of whatsoever. We can understand the mathematics perfectly well, tracing the pattern and following the logical rules of topology, yet when we attempt to actually visualize this object in our mind's eye, something breaks in the process. A gap opens between our intellectual comprehension and our intuitive understanding. What persists is this strange duality where we accept the hypercube net as mathematically valid and useful for theoretical physics and computational geometry, teaching it to students and using it in academic contexts, while simultaneously acknowledging that we cannot genuinely perceive what it represents, creating a normalized acceptance of something we find fundamentally incomprehensible. A paradox we have simply learned to live with and integrate into our knowledge without requiring true understanding or visualization, allowing abstract mathematics to carry meaning beyond the limits of human perception. This acceptance of the invisible becomes especially poignant when we consider that physicists may use hypercube mathematics to describe the actual structure of spacetime itself, suggesting that the 4-dimensional reality we inhabit might be just as foreign to our 3-dimensional perception as the hypercube net is to our intuition, leaving us to wonder whether we are the ones living inside an incomprehensible shape that we can only understand through abstract symbols and equations. Imagine standing in a room and watching a cube rotate slowly before you, turning along the vertical axis so that its faces trade places in a predictable sequence. Now imagine that same cube rotating not just in 3 dimensions, but in a 4th spatial dimension that exists perpendicular to all the directions your eyes can perceive. This is 4-dimensional rotation, or what mathematicians call a tesseract rotating through hyperspace, and attempting to visualize it creates a profound disorientation in the human mind because our brains have evolved exclusively to navigate 3-dimensional space where length, width, and height form the complete inventory of possible directions. When we try to comprehend a rotation that occurs along an axis we cannot see, cannot point toward, and cannot even imagine without abstract mathematical language, we encounter something that should be impossible for human consciousness to grasp, yet our minds persistently strain toward understanding it anyway. The mechanism behind this cognitive struggle lies in the fact that rotation itself is a concept our brains understand intimately through lived experience, and we instinctively try to apply that familiar framework to the unfamiliar scenario of 4-dimensional space. When a 3-dimensional object rotates in 4 dimensions, what we would see from our limited 3-dimensional perspective would appear as a shape that impossibly transforms itself, warping and morphing through configurations that seem to violate the rigid geometry we know to be true. A cube might suddenly appear to distort in ways that no 3-dimensional rotation could produce, its edges stretching and compressing, its angles shifting into configurations that feel geometrically forbidden. Our brains recognize this impossibility and yet continue trying to rationalize it, creating a strange tension between mathematical truth and perceptual reality. What persists in this paradox is the same human impulse that has always driven us to extend our understanding beyond the limits of our senses, the same drive that allowed us to conceive of electromagnetic fields we cannot see and subatomic particles we cannot touch, transforming the invisible and incomprehensible into something that, if not truly understood, at least feels less alien through the application of mathematical language and analogical thinking. Imagine existing in a world where all matter, all objects, all beings exist in only two dimensions, completely flat against an invisible plane with no depth whatsoever, and then consider what would happen if a three-dimensional sphere were to pass through that world, approaching from the direction that the two-dimensional inhabitants cannot perceive or comprehend. As the sphere descends through the flatland plane, the two-dimensional creatures would first observe a single point appearing from absolute nothingness, then watch helplessly as that point expanded into a circle, growing larger and larger with each moment as the sphere continued its passage downward through their dimensional existence. The inhabitants of Flatland would have no framework for understanding what was occurring, no language or mathematical system to describe how a circle could simply expand from nothing and then shrink back to a point before vanishing entirely, because in their two-dimensional reality, nothing exists that could produce such phenomena. This is the essence of dimensional paradox, the way that higher dimensional objects interacting with lower dimensional spaces create logical contradictions from the perspective of those unable to perceive the additional dimension involved. We experience a version of this impossibility in our own three-dimensional existence when we contemplate the properties of four-dimensional objects or higher geometric constructs, spaces that mathematically exist and follow perfect logical rules, but which our brains cannot truly visualize or comprehend because we are inherently limited to perceiving only three spatial dimensions and one temporal dimension. Our minds struggle to construct mental images of tesseracts or hyperspheres or Klein bottles that exist in four dimensions, creating a cognitive dissonance between mathematical truth and perceptual reality. Yet despite this fundamental limitation in our sensory apparatus and our evolved cognitive architecture, we have somehow built entire systems of mathematics and physics that can describe these higher dimensional spaces with perfect precision, allowing us to calculate and predict behaviors of objects we cannot see and spaces we cannot enter. We exist in a peculiar state where we are simultaneously the flatland inhabitants looking up at incomprehensible spheres and the potential observers of dimensions beyond our grasp, trapped between the limitations of our perception and the abstract knowledge that such dimensions almost certainly exist. Imagine holding a piece of rope in your hands, tying it into a knot, pulling it tight, and feeling the absolute certainty that this knot is now permanent, locked into three-dimensional space by the very laws of topology that govern our universe. You could pull on the ends forever and the knot would never come undone, because in three dimensions, the geometry of the knot creates what mathematicians call an invariant, a property that cannot be changed by any amount of continuous manipulation. Yet if we were to introduce a fourth spatial dimension into this scenario, something extraordinary would occur. That knot would simply fall apart. It would untie itself without any force being applied to it, as if the binding property itself had evaporated into possibility. This is not science fiction, but rather a statement about the nature of dimensional space and the way constraints that feel absolute in one dimension become entirely negotiable in a higher one. The knot appears permanent only because we exist in three spatial dimensions where certain topological locks have become irreversible, where the rope cannot pass through itself to undo its own tangles. In four-dimensional space, an extra degree of freedom emerges that allows the rope to rotate through a direction perpendicular to all three dimensions we know, creating a pathway for the knot to slip apart without the rope ever intersecting itself. Our brains struggle to visualize this because we have never experienced four spatial dimensions, and yet the mathematics is perfectly clear. Dimensions add possibilities, not restrictions. We move through life accepting that knots are permanent solutions to binding problems, that once something is tangled, it requires deliberate action to untangle it, and we build entire systems of assumption around this limitation, from secure knots in climbing ropes to the metaphorical knots we describe in our relationships and problems. Yet all of this certainty dissolves at the mere suggestion of an additional dimension, revealing that what feels like an absolute property of reality is actually only an absolute property of our particular dimensional frame. The knot does not truly exist as a permanent entity, but rather as a temporary configuration of space that only appears locked because we cannot access the pathways that would free it. This suggests a profound humility about the nature of constraints themselves. What appears to be an eternal problem may simply be waiting for us to shift our perspective, to find the dimensional leap that reveals the knot was never as binding as we believed. Imagine holding a leather belt in both hands, stretched taut between your palms, and then imagine twisting it once, a full 360-degree rotation, so that the buckle faces away from you in an unnatural orientation. Now here is where the paradox begins. If you were to ask someone to untwist this belt by moving your hands through space without letting go, without crossing your arms in an obvious way, they would tell you it is impossible, that the twist is permanent and locked into the fabric of the belt itself. Yet there exists a seemingly magical procedure, discovered and refined by physicist Paul Dirac, whereby you can rotate one hand in a complete circle while keeping the other hand still, threading your hands through the twisted belt in a specific pattern, and somehow, impossibly, the twist vanishes entirely as if it were never there. The belt becomes untwisted, returned to its original state of repose, even though you have not actually undone the rotation you performed at the beginning. This is the Dirac belt trick, a three-dimensional paradox that demonstrates something profound about the nature of rotation and orientation in space itself. What makes this phenomenon so deeply unsettling is that it reveals a hidden symmetry in three-dimensional space that our intuition completely fails to grasp. When you perform a single rotation of 360 degrees, the object appears twisted, yet a second rotation of another 360 degrees, totaling 720 degrees, allows everything to return to normal through a continuous motion that requires no external intervention. It is as though space itself contains a strange redundancy, a doubling of rotational symmetry that seems to violate everything we understand about how objects should behave. The psychological mechanism underlying why this paradox confuses us so thoroughly is rooted in our evolutionary experience with three-dimensional space, where we expect rotation to be simple and reversible in straightforward ways. Our brains have developed an intuitive physics that works perfectly well for everyday objects and movements, yet this intuition breaks down spectacularly when confronted with the mathematics of rotations in three dimensions, which obey rules that are genuinely alien to our direct sensory experience. Imagine standing in a room and slowly rotating your body in a complete circle, turning your head and torso continuously until you have made one full 360-degree rotation, and you are facing the direction from which you started, and yet your sense of spatial orientation remains intact, and you feel as though nothing has fundamentally changed about your relationship to the room around you. Now consider what happens when you continue rotating beyond this point, continuing to turn through another complete circle, another full 360 degrees, which brings your total rotation to 720 degrees. And in this moment, something peculiar occurs within your consciousness and the way your body processes directional awareness. During the first rotation, you accumulate a sense of momentum and anticipation as you turn, your brain tracking the displacement and preparing for your return to the starting position. And when you complete that initial full circle, you experience a subtle sense of closure and resolution. However, when you deliberately continue past that completion point and execute a second full rotation, the psychological expectation of arrival has already been satisfied, yet your body continues the motion anyway, creating a strange dissociative gap between your conscious awareness and your physical orientation. Your brain has already filed away the completion of the journey home, and yet your muscles and vestibular system continue to process the continuing rotation as if it were a new and separate motion entirely. This peculiar disconnect emerges from the way our neural systems process cyclical motion and spatial memory, relying heavily on the concept of the complete rotation as a meaningful unit of measurement and closure, rather than recognizing rotation as a continuous mathematical spectrum. We have normalized the full circle as the fundamental reset point, the zero point from which all directional awareness restarts, and we have built this assumption so deeply into our intuitive physics that the notion of rotating beyond completion feels conceptually wrong even though mathematically and physically it is completely coherent and unremarkable. Imagine standing before a mirror and raising your right hand, watching as the reflection raises its left hand in return, as if greeting you from some inverted realm that exists only in glass and light. This simple, everyday observation contains within it a profound geometric puzzle that has troubled philosophers and physicists for centuries, because the mirror does not actually reverse your left and right at all, yet we persistently experience it as though it does. And this experience feels so complete, so absolutely true, that we rarely pause to question why our minds accept this reversal as real when the geometry of reflection suggests something far stranger is occurring. When light bounces from your body to the mirror's surface and back to your eyes, the rays follow the laws of physics with perfect precision, reflecting at angles equal to their approach. Yet somehow in this mechanical process, the left-right axis appears inverted, while the up-down and front-back axes remain undisturbed, creating an asymmetrical inversion that should not exist according to pure spatial logic. The paradox deepens when we consider that a mirror does not truly reverse left and right in any absolute sense. Rather, it reverses depth, the axis perpendicular to its surface, and our cognitive system interprets this depth reversal through the lens of our embodied experience, automatically translating the inverted spatial information into the language of left and right that our bodies understand, a translation so habitual and so seamless that we never notice it is happening. We see the image as reversed horizontally because we are creatures who navigate the world through bilateral symmetry, through the constant awareness of our own left and right hands, and so when our brains receive an image with inverted depth, they instinctively rotate it into the coordinate system most relevant to our survival and self-recognition. Which means the reversal is not a property of the mirror, but rather an emergent property of how human consciousness interprets spatial information filtered through a two-dimensional surface. Imagine standing in a vast library where mathematicians have spent centuries working on a single problem that refuses to yield, a task so deceptively simple in its statement that it seems almost insulting to suggest it could be impossible. Yet there it remains, unconquered and perhaps unconquerable, the ancient challenge of squaring the circle, which asks us to construct a square and a circle of equal area using only a compass and a straight edge. Two of the most basic tools available to geometry. The problem itself carries an almost poetic quality because it represents the attempt to reconcile two of the most fundamental shapes in all of mathematics and nature, the circle with its infinite curves and transcendent proportions, and the square with its rational angles and measurable sides, a quest that captivated minds from ancient Greece through the Renaissance and into the modern era, with mathematicians such as Euclid, Archimedes, and countless others dedicating their intellects to cracking what seemed like a puzzle that should have a solution. The psychological mechanism at work here involves what we might call the tyranny of intuition, the deep conviction that because something can be imagined, because we can visualize a square with the same area as a circle, it must be achievable through the tools of geometry, much the same way a child believes they should be able to catch the horizon if they run far enough. And this intuitive sense was reinforced for centuries by the remarkable success of geometric construction solving seemingly difficult problems. Each victory suggesting that the next one was simply awaiting the right clever approach or the right moment of inspiration. What persisted for so long was not ignorance, but rather a fundamental misunderstanding of what mathematicians were working with, because the solution to squaring the circle requires transcendental numbers, specifically the relationship between pi and the construction methods available, a truth that would not be conclusively proven impossible until the late 19th century when Ferdinand von Lindemann demonstrated that pi is not just irrational but transcendental, meaning it cannot be constructed through any finite sequence of compass and straight-edge operations, a revelation that transformed an ancient quest into a mathematical proof of impossibility, yet the problem endures in the cultural imagination as a metaphor for futile effort, for the pursuit of something that cannot exist, for the human tendency to chase elegant solutions to problems that have already been solved, just not in the way we hoped. Imagine standing before an ancient stone cube, perhaps carved from marble or granite, and being asked to construct another cube that contains exactly twice the volume of the original. This problem, known as the Delian problem or the duplication of the cube, emerged from Greek mathematics around 24 centuries ago, and it presents itself as deceptively simple on the surface. If you have a cube with a side length of 1 unit and a volume of 1 cubic unit, the new cube must have a volume of 2 cubic units, which means its side length must be the cube root of 2, approximately 1.2597. The task seems straightforward enough. Simply measure the original cube, calculate the necessary dimensions, and construct the larger cube using those measurements. Yet here lies the profound paradox that captivated mathematicians for centuries. The ancient Greeks, operating under strict constraints, believed that geometric construction must be accomplished using only a compass and straight edge, the fundamental tools of classical geometry. These two instruments, paired together, can accomplish remarkable feats of mathematical creation. They can bisect angles, construct perpendicular lines, create regular polygons, and establish proportional relationships with elegant precision. However, what they cannot do, What was ultimately proven impossible in the 19th century is construct a line segment whose length is the cube root of 2 using only these classical tools. The straightedge provides infinite extension but cannot measure distances, while the compass can transfer measurements and draw arcs but operates only through rotation about fixed points. Together, they form a limited vocabulary of geometric operations. The psychological mechanism underlying the persistence of this paradox involves the way human intuition rebels against mathematical impossibility. When we observe that we can bisect a line segment, we assume we should be able to divide it into any number of equal parts through sufficient iteration. When we can construct the square root of 2 using the diagonal of a unit square, we imagine that cube roots should follow similarly elegant constructions. The mind gravitates toward patterns and assumes that if one operation proves possible, similar operations at higher orders of complexity should remain achievable through expanded effort or cleverness. Furthermore, the problem never ceased to attract attempted solutions throughout history, with mathematicians, architects, and amateur geometers repeatedly proposing new approaches, each confident that they had discovered what countless others had missed. Consider the ancient problem that has captivated mathematicians for over 2,000 years. The attempt to divide any given angle into 3 equal parts using only a compass and a straightedge, the same tools permitted for bisecting an angle, which remains trivially simple by comparison. Picture yourself sitting at a desk with these humble instruments before you, an acute angle drawn on paper, and the seemingly reasonable assumption that if you can fold any angle in half, surely you can fold it into thirds with some clever geometric construction. The straightedge allows you to draw perfect lines, the compass allows you to measure and transfer distances with absolute precision, and yet when you begin to work through the problem, you discover that certain angles yield to your efforts while others stubbornly resist, creating a landscape of partial success that feels almost deliberately designed to frustrate. The psychological mechanism underlying this paradox emerges from our deep intuition about symmetry and divisibility. We have been conditioned since childhood to believe that if an operation is possible at all, then variations of that operation should also be possible, scaling up or down in complexity, but ultimately achievable through sufficient cleverness and effort. The bisection of an angle appears straightforward and elegant, so our minds naturally extrapolate that trisection should follow logically, merely requiring a more intricate approach or perhaps a technique we have not yet discovered. We normalize this expectation because we live in a world where most divisions are arbitrary matters of iteration. If you can cut something in half, you assume you can continue cutting to achieve thirds, fourths, or any fraction whatsoever. Yet the mathematical truth, finally proven in the 19th century through Galois theory and field extensions, reveals that angle trisection using compass and straightedge alone is genuinely impossible for most angles, not because we lack cleverness, but because the underlying algebraic structure of the problem transcends the geometric capabilities of these tools, a reality that persists in our collective consciousness as a kind of beautiful scar. A permanent reminder that our intuitions about space and division sometimes betray us. This impossibility proof stands apart from other mathematical limitations because it answers not merely whether something can be done, but rather explains why the universe of geometry forbids it, transforming a failed construction into a profound statement about the nature of mathematical reality itself. In 1894, the German mathematician David Hilbert posed a deceptively simple question at the International Congress of Mathematicians, one that would occupy mathematical minds for decades to come. If you take 2 polyhedra, 3-dimensional shapes with flat faces like a cube or a pyramid that possess the same volume, can you always decompose one into a finite number of smaller pieces and reassemble those pieces to form the other shape, a principle known as equidecomposability? It seems intuitively obvious that if 2 solid objects contain the same amount of space within them, you ought to be able to cut one apart and rearrange it into the other, much as you can do with 2 flat polygons of equal area on a sheet of paper. This intuition comes from our lived experience with physical objects and our understanding of how volume works, the sense that matter is conserved and malleable when we manipulate it. Yet Hilbert suspected something deeper, something more troubling about the nature of 3-dimensional space itself. The puzzle reveals that while this decomposition principle holds true for 2-dimensional shapes, allowing any polygon of a given area to be transformed into any other through finite cutting and pasting, the same guarantee simply does not extend into 3 dimensions. This asymmetry between two-dimensional and three-dimensional space creates a kind of spatial paradox, a place where our intuitions about how objects should behave fundamentally fail us. What makes Hilbert's third problem so psychologically disorienting is that it challenges our belief that volume is the only thing that matters when comparing solids, that equal volumes should guarantee interchangeability through geometric manipulation. We have internalized the idea that space is fundamentally uniform and that geometry obeys consistent rules regardless of dimension. Yet this problem exposes a hidden discontinuity, a boundary beyond which our assumptions collapse. The resolution came in 1901 when the mathematician Max Dehn discovered that polyhedra require an additional invariant beyond volume to determine equidecomposability, a numerical value now called the Dehn Invariant, which somehow encodes geometric information that volume alone cannot capture. This finding persists in modern mathematics as a quiet reminder that our intuitions about space, however reasonable they seem, remain incomplete, that the universe of geometry contains depths we cannot fully access through simple observation and reasoning. Consider the seemingly straightforward problem that mathematicians posed centuries ago. If you have a polyhedron, a three-dimensional solid bounded by flat faces, can you always cut it into pieces and rearrange those pieces to form a different polyhedron of equal volume? This question, which feels like it should have a simple yes answer, leads us directly into one of geometry's most subtle and elegant paradoxes, one that reveals how our intuitions about space and equivalence can systematically mislead us. The Dehn invariant, named after mathematician Max Dehn, who discovered it in 1900, provides the mathematical machinery to prove that certain polyhedra cannot be rearranged into other polyhedra despite having identical volumes, which seems to violate our basic spatial reasoning about how objects should behave. The paradox emerges from the fact that we naturally assume volume is the only relevant property, the only measure that matters when determining if two solids are truly equivalent in a meaningful geometric sense. But Dehn revealed that there exists an additional invariant, a hidden mathematical property that remains unchanged through cutting and rearranging, just as volume does, yet it can differ between two polyhedra of equal volume. This invariant is constructed from the edges of the polyhedron, specifically from careful combinations of edge lengths and the dihedral angles between adjacent faces, combined in a way that seems almost arbitrary until you understand its purpose. When you cut a polyhedron, you create new edges along the cutting surface, and these new edges come with their own angles, and the Dehn invariant accounts for all of this with remarkable precision, tracking information that seems geometrically invisible yet remains stubbornly present. The psychological mechanism that makes this paradox so disorienting stems from our reliance on volume as the primary measure of spatial magnitude, a heuristic that served us well in everyday life but fails to capture the full geometric complexity of three-dimensional space. We have normalized the idea that equal volume equals essential equivalence, that two containers of the same volume can always be transformed into one another through physical rearrangement. Yet the Dehn invariant demonstrates this intuition is simply false. It is a beautiful illusion maintained by our limited perceptual apparatus and our ancestral unfamiliarity with abstract mathematical space. Imagine a perfect circle drawn on a piece of paper and beside it a square with the same area. In the classical geometry we learned in school, these two shapes are fundamentally distinct, separated by the very nature of their boundaries, and converting one into the other through construction alone is considered impossible. Yet in 1924, the Polish mathematician Alfred Tarski posed a question that seemed almost absurd. Could a circle be divided into finitely many pieces and reassembled into a square of equal area? The answer, which emerged from decades of mathematical investigation, was an unexpected yes, a result so counterintuitive that it challenges our deepest assumptions about what shapes fundamentally are and whether the properties we think are immutable actually hold any real meaning at all. The mechanism underlying this paradox rests upon an idea that most people never encounter in their everyday mathematical thinking, a concept called equidecomposability, which states that two geometric figures can be considered equivalent if one can be cut into a finite number of pieces, and those pieces can be rearranged to form the other shape without overlapping or leaving gaps. What makes Tarski's discovery so profound is that it demonstrates the circle and square are equidecomposable despite their obvious visual and structural differences. And the reason this works involves allowing the pieces themselves to be extraordinarily complex in ways that our intuition about geometry simply never prepared us for. The pieces required are so fragmented, so infinitely intricate in their boundaries, that they exist at the very edge of what we can even call a geometric object, hovering in a conceptual space between pure mathematics and philosophical abstraction. What persists most fascinatingly is how we continue to accept this result while simultaneously maintaining our intuitive sense that circles and squares are fundamentally different categories of being. And we have normalized this contradiction by compartmentalizing our understanding into distinct levels of rigor, acknowledging that in formal mathematics, such transformations are possible while in practical geometry, they remain impossible. And this strange duality reveals something profound about how mathematics itself is not a description of reality, but rather a language whose meaning shifts depending on the rules we choose to apply. And in this recognition, we find ourselves suspended between two truths that cannot be reconciled, except through acceptance of ambiguity itself. Imagine standing in front of a geometric shape that appears to be a perfect equilateral triangle, drawn on a piece of paper with clean, sharp lines. And then imagine being told that this triangle can be cut into 4 separate pieces that, when rearranged through only rotation and translation, without any overlap or gaps, form a perfect square of identical area. And then imagine the profound unsettling feeling that arises when you realize this transformation is not merely theoretically possible, but actually demonstrable through physical manipulation. A puzzle first conceived and solved by Henry Dewdney, a legendary British mathematician and puzzle creator in 1902, who discovered that by making 3 precise cuts through the triangle, you could create pieces that fit together perfectly as a square. A square that contains the exact same area as the original triangle despite appearing to be a fundamentally different shape. The psychological mechanism underlying our shock at this discovery emerges from our deeply ingrained categorical thinking about geometric forms, the way our minds have been trained through years of mathematics education to view shapes as fixed and immutable containers of space. So when we encounter the haberdasher's puzzle, our brains rebel against the evidence before us because we have internalized an assumption that equilateral triangles and squares are essentially different entities that cannot share the same spatial volume without something being added or removed. The remarkable aspect of this puzzle lies not in its mathematical complexity, but in how it exposes the gap between our intuitive geometric understanding and the actual properties of space. For area conservation across different shapes challenges our visual expectations in profound ways, and yet we have normalized this paradox almost completely in modern mathematical education, treating it as merely another example of geometric dissection rather than as the conceptual revelation it truly represents. Imagine a perfect square, a shape so fundamentally simple and unified that it represents completeness itself. And then imagine dividing that single square into a collection of smaller squares, each one different in size, each one fitting together with mathematical precision like a puzzle where no 2 pieces are the same dimension. And this act of subdivision, this transformation of one into many while maintaining the overall square shape, is called squaring the square. A geometric paradox that seems to violate our intuitive sense of how shapes should behave when we break them apart and rearrange them. The real phenomenon begins with the question of whether such a division is even possible, whether you can take a single square and partition it into a finite number of smaller squares, all of different sizes, with no remainder and no overlap, creating what mathematicians call a perfect squared square, and remarkably the answer is yes, though it took centuries for mathematicians to prove this was achievable, the first perfect squared square being discovered in 1938. Containing exactly 21 smaller squares of varying dimensions, all fitting together with absolute geometric precision within the boundary of the larger square. The psychological mechanism that makes this paradox so compelling to contemplate rests in our expectation that simplicity should remain simple, that a unified whole divided should produce something less harmonious, and yet the squared square demonstrates that even in division, perfect order can be maintained, that fragmentation does not necessarily lead to chaos, and this challenges our intuitive understanding of how parts relate to wholes, for when we see the completed squared square, our eyes struggle to accept that what appears to be a chaotic arrangement of rectangles and squares of different proportions is actually a perfectly balanced and mathematically flawless construction, each dimension carefully calculated so that the entire configuration resolves into a perfectly square boundary, and our sense of spatial harmony becomes confused because we expect either total unity or total disorder, not this middle ground where complexity and perfection coexist. Imagine yourself standing in your living room with a sofa that you need to move into an adjacent hallway, and the hallway makes a sharp 90-degree turn, creating a narrow passage where the corridor width suddenly changes, forcing any large object to navigate through a constrained geometric bottleneck that would seem to have clear physical limitations. This is the fundamental scenario that mathematicians have contemplated for decades, wondering what is the largest sofa that could possibly fit through such a configuration without being tilted, rotated, or manipulated in ways that would damage it or require disassembly. The question seems practical at first, rooted entirely in the physical world of furniture and architecture, yet it rapidly transforms into one of the most perplexing unsolved problems in mathematics, where the answer remains elusive despite extensive computational efforts and brilliant theoretical work. The mechanism behind this puzzle relies on the principle of optimization within constrained spaces, where you must find the shape that maximizes area while remaining capable of rotating through a right-angled corridor with specific width measurements. The sofa cannot simply be a rectangle, because a rectangular shape offers no flexibility when maneuvering around the corner. Instead, it must be a shape that can somehow twist and navigate through the turn while maintaining maximum possible surface area, perhaps something resembling a curved form that adapts to the geometric demands of the passage. Mathematicians have developed increasingly sophisticated approaches to approximate the optimal sofa shape, discovering configurations that include concave indentations and asymmetrical curves, yet no definitive proof exists establishing what the theoretical maximum truly is. We have normalized our uncertainty about this problem by treating it as an elegant mathematical curiosity rather than acknowledging the deeper discomfort it creates, that a situation so grounded in everyday experience remains fundamentally beyond our complete understanding and precise calculation, suggesting that even in our managed spaces and carefully constructed environments, there are dimensions of optimization and spatial relationship that escape our full comprehension. Imagine a long corridor in an old building, one that turns sharply at a right angle, and you are attempting to move a ladder through this passageway without tilting or rotating it in ways that would damage the walls or the ladder itself. And this simple task becomes a profound mathematical puzzle that has haunted engineers and mathematicians for over a century. The ladder must navigate the turn while remaining roughly horizontal, which means it must pass through a configuration where it touches the outer corner of the turn. And at this critical moment, the ladder forms a kind of diagonal bridge across the space, one end resting against one wall and the other end resting against the opposite wall, with the corner itself becoming a fulcrum point around which the entire problem revolves. The question that emerges from this scenario is deceptively simple. What is the longest ladder that can physically navigate such a turn without getting irreversibly stuck? And the answer is not a fixed number, but rather depends on the widths of the two corridors meeting at the corner, creating what mathematicians call the moving sofa problem's narrower cousin, the ladder problem. As you mentally rotate a ladder through this corner, keeping it level and parallel to the ground, you realize that the constraint is not just one rigid position, but rather a continuous family of positions, each position showing the ladder at a different angle as it pivots around that outer corner. And the critical moment arrives when the ladder reaches its most vulnerable configuration, the angle at which it comes closest to becoming wedged, unable to proceed further in either direction. The psychology behind why this problem persists in our thinking despite its apparent mundanity lies in the disconnect between our intuitive spatial reasoning and the actual geometric constraints at play. Our brains want to believe that a ladder should simply slip through a corner as long as it is not too long, yet the mathematics reveals something far more subtle and counterintuitive. That the maximum length depends on a complex optimization involving the width of both corridors and their angular relationship. Imagine yourself in a perfectly dark room where you cannot see anything around you, and in this room, you are holding a single sphere, a perfect ball of uniform density and size. Now imagine that you could somehow hold additional identical spheres around this central sphere, each one touching it at exactly one point, like kisses pressed gently against its surface. The question that emerges, deceptively simple on the surface, is this: how many spheres can you arrange around your central sphere such that each one touches it and none of them overlap with one another? This is the kissing number problem, and it has haunted mathematicians for centuries because the answer changes depending on the dimensionality of the space you are working within. In three-dimensional space, which is the space we inhabit and perceive directly, the answer is 12, though proving this rigorously took mathematicians decades of intensive work. Picture 12 golden spheres arranged in a perfect three-dimensional configuration around a central sphere, each one kissing that center point without disturbing its neighbors, and you begin to grasp the geometric elegance of this arrangement. Yet here lies the profound disorientation. In lower dimensions, the answer is different, and in higher dimensions, the mathematics becomes even more bewildering. In 2 dimensions on a flat plane, you can only fit 6 circles around a central circle, a comfortable, comprehensible number. But move to 4 dimensions, and suddenly the kissing number becomes 24, a number that defies our intuitive visualization. The human mind evolved to navigate three-dimensional space, to understand how objects fit together, to predict collisions and arrangements in the world around us. When we think about spheres touching, we naturally extrapolate from our experience with three-dimensional objects. Yet mathematics reveals that our intuitions fail us the moment we venture beyond the familiar 3 dimensions. The kissing number problem persists in our collective consciousness as a gentle reminder that spatial reasoning, that seemingly most fundamental aspect of human cognition, is deeply limited to the specific dimensional structure of our environment. We have normalized this limitation by simply refusing to think about higher dimensions in any concrete way, treating them as abstract mathematical constructs rather than genuine extensions of spatial reasoning. Imagine a vast warehouse filled with identical spheres, stacked and arranged in three-dimensional space with mathematical precision, where the challenge becomes not how to arrange them, but understanding the most efficient way possible to fill the void between them, a problem that has haunted mathematicians and physicists for centuries. Ever since Johannes Kepler observed that spheres, those perfect geometric forms, cannot tessellate completely without leaving gaps, and that the most efficient arrangement appears to follow a pattern seen in nature itself, in the way oranges stack at market stalls, in the crystalline structures of metals, in the very architecture of atoms clustering together. The question Kepler posed in the 1600s was elegantly simple yet profoundly complex. Given unlimited spheres of uniform size, what arrangement allows you to pack them most densely, leaving the smallest possible empty space between them? And his conjecture suggested that the densest packing would achieve approximately 74% efficiency, meaning about 26% of space would remain perpetually empty no matter how carefully you arranged them. What makes this paradox so psychologically unsettling is that for nearly 400 years, despite its apparent simplicity, despite its obvious practical applications in chemistry and materials science and logistics, mathematicians could not definitively prove that Kepler was correct, operating instead on intuition, observation, and reasonable assumption rather than rigorous mathematical certainty, conducting experiments with physical spheres, studying natural crystal formations, and running computational simulations, yet always falling short of absolute proof, creating a strange suspension where the answer seemed obvious yet remained technically unverified, where intuition and mathematical rigor diverged, where the practical world and pure mathematics spoke different languages. Imagine standing in a room where the floor extends infinitely in all directions, covered entirely by tiles of just 2 shapes, one thick rhombus and one thin rhombus, each adorned with colored edges that must match perfectly where they meet. At first glance, this appears to be a normal tiling pattern, a mathematical arrangement that should repeat itself predictably like the tiles in your bathroom or the bricks on a street. Yet as you walk across this impossible floor, you begin to notice something profoundly unsettling about its nature. The pattern never repeats itself, not anywhere, not even if you walk for miles in any direction, and this is not a failure of the pattern, but rather its fundamental defining characteristic. This is the Penrose Tiling, discovered by mathematician Roger Penrose in the 1970s, a geometric arrangement that achieves what was previously thought impossible. A perfectly ordered, aperiodic tiling of the entire plane using only 2 shapes with matching rules that force an infinite, non-repeating pattern into existence. The mechanism underlying this paradox rests on the mathematical constraint that the colored edges impose upon the tiles themselves. When you place a rhombus on the floor, its edges are painted in specific colors, and the rule is absolute. Only edges of matching colors may touch one another. This constraint cascades through space in a way that builds upon itself, where each tile you place determines the possibilities for its neighbors, which in turn determines the possibilities for their neighbors, spreading outward in chains of logical necessity that somehow prevent any repeating motif from ever stabilizing. The angles embedded within the Penrose rhombuses relate to one another through the golden ratio, that mysterious constant that appears throughout nature and mathematics, and this proportion becomes the silent architect that choreographs an infinite dance of tiles that never returns to a previous position. The tiling achieves what mathematicians call quasi-periodicity, a state of being orderly and structured while simultaneously remaining forever aperiodic, forever refusing to collapse into simple repetition. What makes this situation persist as a paradox in our minds is that we have become so accustomed to patterns that repeat, to the idea that order implies periodicity, that the existence of an eternally ordered yet eternally non-repeating structure seems to violate something fundamental about how we understand organization and mathematics itself. Imagine standing in a vast hall where a single shape has been scattered across an infinite floor, repeating endlessly in every direction, covering every gap and touching every corner with perfect precision, yet never once settling into a pattern that your mind can predict or your eyes can follow as it moves away from you. This is the Aperiodic Monotile, a shape discovered in 2023 that accomplishes what mathematicians spent decades believing to be impossible. A single tile, just one solitary form, capable of covering an entire plane completely without gaps or overlaps, while simultaneously refusing to create any repeating pattern whatsoever. The shape itself, often called the hat or Einstein tile, possesses an irregular, almost organic quality, with curved and straight edges meeting at angles that seem almost arbitrary, yet this apparent randomness is precisely what grants it its extraordinary power. When you attempt to tile a surface using identical copies of this shape, you find that it fills space perfectly, every boundary aligning seamlessly with its neighbors, every corner matching every other corner, yet the overall configuration never settles into regularity, never repeats in the way that diamonds or hexagons or squares inevitably do when given enough space to establish their periodic rhythms. The psychological mechanism underlying our shock at this discovery stems from our deep intuition about symmetry and order. For centuries, we have observed that any shape capable of tiling the plane either produces periodic patterns like the honeycomb or remains fundamentally incomplete and insufficient. Our brains, evolved to recognize patterns and predict repetition, naturally assume that perfect space filling must also mean perfect regularity, that these two properties are inseparably linked, yet the aperiodic monotile shatters this assumption by divorcing efficiency from predictability. What persists despite having seemed logically impossible is our gradual acceptance that the universe operates according to principles far more subtle than simple symmetry, that constraint and chaos need not be opposites, but can instead dance together in configurations that fill space completely while remaining eternally unpredictable. A reminder that order and disorder exist not as absolutes, but as states that can interweave in ways our pattern-seeking minds have only recently learned to acknowledge. Imagine a single geometric shape, a curved tile with 9 sides that possesses an almost impossible property. It can tile an infinite plane in a spiral pattern that never closes, never repeats, and never creates a traditional lattice structure that your mind expects from a repeating pattern. This is the Voderberg spiral tiling, discovered in 1968 by Heinz Voderberg, a shape that defies our intuitive understanding of how space should be organized when filled completely and without gaps. The tile itself appears deceptively simple at first glance, resembling something between a pinwheel and a stretched parallelogram with gentle curves, yet when positioned correctly with its replicas, it generates a mesmerizing spiral arms that extend outward toward infinity like a nautilus shell scaled to encompass all available space. The spiral tiling creates a peculiar visual effect where your eye continuously traces along concentric rings and spiraling arms, following paths that seem to lead somewhere definite but instead dissolve into endless repetition at different scales, creating a sense of motion within a static image. The psychological mechanism at work here involves our brain's deep expectation that repeating patterns must eventually return to their starting configuration, that periodicity and closure are fundamental laws of tessellation. Yet the Voderberg spiral violates this expectation entirely while maintaining perfect geometric integrity with no overlaps and no gaps whatsoever. We experience a cognitive dissonance when confronted with a shape that obeys all the mathematical rules of space filling, while simultaneously breaking the symmetry rules we have internalized through years of encountering regular tilings like hexagons, squares, and triangles that arrange themselves into predictable, comprehensible patterns. Despite this fundamental contradiction between our expectations and mathematical reality, we have simply absorbed the Voderberg tiling into our understanding as merely another interesting geometric curiosity, rather than a profound challenge to how space itself can be organized, treating it as an exception to rules rather than evidence that our intuitive rules were never universal to begin with. Yet this very discovery reveals something profound about mathematics itself, that the universe permits infinite organizational schemes beyond what our evolved intuitions suggest, and that genuinely novel geometric possibilities await discovery not because they violate mathematical law, but because they operate within a far richer space of possibilities than our everyday experience has prepared us to imagine. Consider the fundamental constraint that governs the architecture of crystalline matter itself, a rule so deeply embedded in the fabric of three-dimensional space that it seems to emerge from the very laws of geometry rather than mere mathematical convenience. Five-fold rotational symmetry, the kind of perfect balance we see in starfish and the petals of certain flowers, appears to be categorically forbidden when we attempt to tile a flat plane with identical shapes, or to construct a three-dimensional lattice where atoms arrange themselves in a perfectly repeating pattern. The reason is elegantly simple, yet profoundly constraining. A flat surface can only be completely filled with repeating tiles if those tiles possess two-fold, three-fold, four-fold, or six-fold symmetry, never five-fold. If you try to arrange regular pentagons across an infinite plane with no gaps or overlaps, you will inevitably encounter empty spaces that no pentagon can fill, a geometric impossibility that seems almost cruel in its absoluteness. The same prohibition extends into three dimensions, where the restriction becomes even more severe, and for decades this constraint stood as an unassailable law of crystallography, taught in universities as a fundamental truth about the organization of matter itself. Yet in 1984, a discovery emerged that shattered this certainty when scientists observed quasicrystals, exotic materials exhibiting five-fold symmetry and even 10-fold and 12-fold symmetries that were deemed impossible by the crystalline rules everyone had accepted. These materials do not form perfect repeating lattices in the classical sense, but instead create patterns that are ordered and aperiodic, repeating according to mathematical rules like Fibonacci sequences and golden ratios rather than simple geometric translation. What makes this paradox so psychologically disorienting is that we internalize the impossibility so completely that the violation of it feels like a breach of reality itself, as though the universe has revealed that what we thought was a fundamental law of space was merely a limitation we had failed to transcend. The mind struggles to reconcile this because the forbidden pattern now exists in laboratories and museums, crystalline structures we can touch and measure, yet they still cannot be described by the classical symmetry groups that organize all conventional materials. Imagine a three-dimensional shape that seems to violate the most fundamental assumptions about how solid objects can exist in space. A polyhedron discovered in 1977 by Hungarian mathematician Lajos Szilassi that possesses 7 faces, each one of which touches every single other face along a shared edge, creating a configuration so geometrically improbable that it challenges our intuitive understanding of spatial topology and the very nature of adjacency itself. This polyhedron is not merely an abstract mathematical curiosity, but rather a concrete geometric structure that demonstrates how the rules governing shared boundaries in three-dimensional space can produce arrangements that feel almost impossible to the human mind, accustomed to everyday objects like cubes and pyramids, where faces meet only their immediate neighbors. The Szilassi polyhedron has 7 quadrilateral faces, meaning four-sided surfaces, and the defining characteristic that makes it so paradoxical is that every single face shares at least one edge with all 6 other faces, creating a complete graph in topological terms, a configuration where the notion of separation and isolation between faces becomes entirely meaningless. When you attempt to visualize this shape or construct it from paper or wire, the experience becomes meditative and deeply disorienting because your brain struggles to maintain a coherent three-dimensional model of something that seems to contradict spatial logic, where each face somehow manages to be adjacent to every other face without any face being somehow disconnected or floating, isolated in space. The mechanism underlying this geometric possibility relates to how we define adjacency and connectivity in topology, where what matters is not the intuitive notion of being nearby, but rather the mathematical relationship of sharing a boundary, and the Szilassi Polyhedron demonstrates that in higher dimensional thinking and non-Euclidean spatial configurations, adjacency relationships can become far more complex and interconnected than our everyday experience with familiar objects would suggest. Imagine holding a three-dimensional shape so geometrically peculiar that it seems to violate the very rules we use to understand solid objects, a form that exists in mathematical space with such unusual properties that mathematicians themselves took decades to verify its legitimacy once it was formally described in 1949 by the Hungarian mathematician Ákos Székely. The Császár polyhedron is a non-convex polyhedron with 14 vertices, 21 edges, and 7 faces, where each face is a triangle, making it what mathematicians call a toroidal polyhedron because its topology resembles that of a torus or donut rather than a simple sphere or conventional solid. What makes this shape genuinely unsettling to contemplate is that every single vertex connects to every other vertex through an edge, meaning that if you were to stand at any corner of this polyhedron and trace the network of connections, you would eventually find a direct path to all 13 other vertices. A property that creates an extraordinarily dense and interconnected geometric web where separation becomes almost impossible, and the usual distinctions between inside and outside become fundamentally ambiguous. The psychological mechanism that allows us to accept this shape without immediate cognitive rejection stems from our deep reliance on visual and spatial intuition developed through millions of years of evolution in three-dimensional Euclidean space. Intuition that is fundamentally unprepared to grapple with topologically complex surfaces that cannot be easily embedded in our standard understanding of reality. When we examine the Császár polyhedron, our brains struggle because it occupies a strange intermediate space between mathematical abstraction and potential physical reality, a realm where the rules governing connection and proximity operate according to principles that seem simultaneously logical and impossible, where the highly regular distribution of vertices and edges creates a kind of satisfying mathematical symmetry even as it defies our intuitive grasp of how three-dimensional objects should behave. What persists most strikingly is our acceptance of such paradoxical shapes as legitimate mathematical objects despite their apparent violation of our experiential understanding, an acceptance rooted in our recognition that mathematical truth operates independently of our immediate sensory perceptions, that the universe contains structures and relationships far stranger than our evolutionary heritage prepared us to comprehend intuitively. Imagine a shape that appears to exist in three-dimensional space, a solid form with vertices and edges and faces that seem perfectly legitimate at first glance, yet possesses an impossible property that defies one of the most fundamental assumptions we make about geometry itself. This is the Schönhardt polyhedron, a construction discovered in 1927 by the mathematician Erich Schönhardt, which presents us with a profound paradox about the nature of solids and the spaces they can or cannot contain. The polyhedron begins as something recognizable, a triangular dipyramid or triangular bipyramid, which is simply two triangular pyramids joined base to base, creating a shape with 6 vertices, 9 edges, and 5 triangular faces arranged in a perfectly sensible manner. However, Schönhardt made a crucial and elegant modification to this otherwise ordinary form by twisting the top pyramid slightly relative to the bottom one, rotating it just enough so that certain structural relationships fundamentally change their character. This modest rotation, this gentle spiraling motion applied to one half of the shape relative to the other, transforms the polyhedron into something that cannot be triangulated from any single interior point, a property so counterintuitive that it seems to violate our basic understanding of how three-dimensional solids must behave. The mechanism behind this paradox lies in the relationship between convexity and decomposability, between whether a shape can be divided into simpler pieces and what those restrictions tell us about its fundamental nature. When you examine the Schönhardt polyhedron carefully, you discover that while it appears to be a valid three-dimensional solid with a well-defined interior and exterior, it actually possesses no internal point from which you could triangulate the entire structure into smaller tetrahedra without some of those tetrahedra extending outside the original shape. This means that despite looking like a unified solid object, the polyhedron cannot be decomposed into simple pyramids from any vantage point within its own space, creating a situation where the shape fails a test that every truly valid polyhedron should pass. Imagine you have a flexible polyhedron, a three-dimensional shape constructed from rigid polygonal faces connected along flexible edges, and you begin to squeeze and expand it like a bellows, watching as its form transforms and contorts in ways that seem to violate our most basic intuitions about space and volume. The Bellows theorem, proven rigorously in 1997 by Sabatov and refined through subsequent mathematical investigations, reveals a truth so counterintuitive that it fundamentally challenges how we understand the relationship between shape and size. As you flex this polyhedron, deforming it continuously while keeping all face areas constant, the total volume remains absolutely unchanged, frozen in place as if locked by invisible geometric laws. When you squeeze one region inward, expecting the volume to decrease, another region must bulge outward by exactly the right amount to compensate, creating a perfect balance that preserves the three-dimensional space occupied regardless of how dramatically the shape appears to transform. This theorem emerges from the deeper mathematical principle that volume in these flexible structures depends not on the current configuration, but solely on the edge lengths and face areas, which remain fixed throughout the deformation process. The psychological mechanism behind our confusion arises from our everyday experience with inflatable objects and collapsible containers, where changing shape invariably means changing volume, and this lived experience has become so deeply embedded in our spatial intuition that we find ourselves genuinely shocked when mathematics reveals a scenario where transformation occurs without volumetric consequence. We have normalized the idea that flexibility equals capacity for expansion or compression, yet the Bellows theorem demonstrates that these two properties exist in completely independent dimensions, that a shape can undergo dramatic metamorphosis while maintaining its three-dimensional footprint with mathematical precision, a reality that persists in the mathematical realm regardless of how counterintuitive it feels to our embodied minds. The practical implications extend beyond pure mathematics into materials science and engineering, where understanding this principle allows designers to create structures that can reshape themselves for different purposes without sacrificing internal capacity, demonstrating that nature's geometric constraints often permit far greater flexibility than our intuitions would suggest. Consider two stacks of coins lying on a table before you, one perfectly aligned in a neat tower and the other pushed and shifted so that each coin tilts at a different angle, creating a lining, irregular formation that seems almost chaotic in its arrangement. According to Cavalieri's principle, named after the Italian mathematician Bonaventura Cavalieri, who formulated this concept in the 1700s, these two stacks possess exactly the same volume despite their vastly different appearances and organizations. The principle states that if two solids have the same height and their cross-sections taken at every level are equal in area, then the volumes of those solids must be identical, regardless of how distorted or rearranged the internal structure becomes. The psychological mechanism operating within our spatial intuition rebels against this notion because we have evolved to perceive volume as something intrinsically connected to order and regularity, to alignment and symmetry. When we see something shifted and warped, our minds unconsciously anticipate that its internal quantity must have somehow changed, that the disorder itself represents a loss or gain of substance. Yet the mathematics proves indifferent to our visual expectations. If you slice through both coin stacks at the exact same height, the cross-section reveals the same total area of coin material in both cases, and this equivalence holds true at every possible height without exception. What makes Cavalieri's principle particularly unsettling is how it demonstrates that volume is fundamentally indifferent to shape and configuration. That substance exists in some realm independent of the geometric presentation we assign to it. We have normalized this principle within mathematics and physics, teaching it in classrooms as though it were an obvious truth. Yet the deeper we contemplate it, the more our intuitive understanding of three-dimensional space seems to fracture and reform around this strange revelation that disorder and order contain identical quantities of being within them. This principle extends far beyond coins. A sphere and a cylinder of equal height and cross-sectional area possess identical volumes, a fact that seems to violate our sense of geometric propriety, yet the mathematics remains unyielding in its logic, forcing us to confront the possibility that our visual perception has fundamentally deceived us about the nature of physical reality itself. Imagine three cylinders passing through space, each one oriented along a different axis, each one perfectly perpendicular to the others, each one intersecting at the exact same central point with the same radius. And as they pass through one another, the region where all three cylinders occupy the same space creates a form so geometrically impossible that it seems to violate our fundamental understanding of how three-dimensional shapes can exist. This intersection is called the Steinmetz solid, named after the mathematician Charles Steinmetz, who first described its properties in the early 20th century. And it represents one of those rare moments in geometry where intuition and mathematics arrive at a conclusion that feels fundamentally wrong to our visual perception. The solid that emerges from this three-way intersection appears almost organic, with curved surfaces that bow inward, creating what looks like four identical petals or lobes that seem to fold into themselves. And the edges where these surfaces meet form perfectly symmetrical curves that flow together, as if sculpted by some invisible hand following laws of physics we cannot quite grasp. What makes this shape so conceptually troubling is that it challenges our ability to mentally construct three-dimensional objects. Because while we can imagine two intersecting cylinders relatively easily, the addition of a third cylinder passing through at a right angle to both creates a region of overlap that our spatial reasoning struggles to visualize. And even when we understand the mathematics completely, when we attempt to actually picture the shape rotating through space, our minds seem to rebel against the configuration. The Steinmetz solid represents a genuine gap between mathematical knowledge and geometric intuition, a place where we can prove something exists and describe its properties with absolute precision, yet simultaneously fail to achieve a coherent mental visualization of it, and perhaps this is the deepest paradox it offers us. The knowledge that some spaces in mathematics are simply beyond the reach of human spatial imagination, no matter how carefully we study them, existing in a realm of pure mathematical truth that our three-dimensional minds can only access through equations and abstract reasoning rather than through the lived sensory experience we normally rely upon to understand shape and volume. Yet this very limitation reveals something profound about consciousness itself, that the deepest truths of mathematics often reside not in what we can see, but in what we can only know through the rigorous language of equations and logical proof. Imagine a bounded space filled with circles, where each circle rests perfectly tangent to its neighbors, and between every gap where three circles touch, another circle fits with mathematical precision, and then between the gaps created by those new circles, even smaller ones emerge, continuing infinitely inward toward ever-diminishing scales that your eye cannot follow, but your mind can still conceive of abstractly. This is the Apollonian gasket, a geometric construction discovered by the ancient mathematician Apollonius of Perga, and it represents one of the most profoundly unsettling demonstrations of infinite complexity arising from simple, orderly rules. The gasket begins with three mutually tangent circles, and then the fundamental principle unfolds. Wherever three circles touch one another at a single point, there exists a mathematically unique fourth circle that is tangent to all three, fitting perfectly into the curved triangular space between them. Once you place this fourth circle, you have created new gaps, new spaces bounded by three circles, and each of these spaces demands its own fourth circle to fill it. And then those circles create further gaps, and the process repeats infinitely, generating an impossibly dense packing of circles that never quite fills the entire space, yet grows exponentially more complex with each iteration. What makes the Apollonian gasket psychologically disorienting is that it embodies a paradox of finiteness and infinity operating simultaneously within a bounded region. For the original space is finite and enclosed, yet within it contains infinitely many circles, each smaller than the last, compressing toward an intricate, infinitely detailed boundary that fractal geometry now recognizes as possessing a dimension between 1 and 2. The mechanism that allows this impossibility to exist is the mathematical relationship known as Descartes' circle theorem, which defines precise curvature values for any four mutually tangent circles, meaning that once you establish your initial three circles, every subsequent circle is not merely suggested, but absolutely determined by geometry itself, allowing infinite circles to pack into finite space through ever-decreasing scale. Imagine a landscape populated entirely by circles, each one tangent to a horizontal line below it, and imagine that among these circles exists a precise mathematical relationship so intricate and so perfectly ordered that it seems impossible such arrangement could emerge from simple rational numbers alone. This is the world of Ford circles, a geometric construction named after the American mathematician Lester Ford, who first described them in the 1920s, though the circles themselves seem to exist in a realm beyond time, waiting to be discovered rather than invented. Each Ford circle corresponds to a fraction expressed in lowest terms, and the position and size of each circle follows an elegant rule. If a fraction p divided by q is reduced to its simplest form, then the corresponding Ford circle has its center at coordinates p divided by q on the horizontal axis, and at a height determined by 1 divided by 2 times q squared, while the radius of that circle is precisely 1 divided by 2 times q squared as well. What emerges from this mathematical framework is a landscape where countless circles nestle together in a pattern of extraordinary harmony, each one touching the baseline, and where smaller circles fit into the gaps between larger ones with perfect precision, creating an infinite regression of tangency that recalls the branching patterns found in nature, the way roots spread through soil or the way tributaries merge into rivers. The psychological experience of contemplating Ford circles involves confronting the strange sensation that mathematics is not merely describing reality, but rather revealing an architecture that seems almost conscious in its perfection, as though the universe has encoded efficiency and balance into the very fabric of numerical relationships. We tend to think of mathematics as an abstract human invention, symbols we created to help us navigate the world, yet Ford circles demonstrate a kind of inevitability, a sense that if numbers themselves existed before humans ever conceived of them, they would arrange themselves in precisely this manner, suggesting that mathematical truth operates independently of our awareness of it. The circles fit together without gaps or overlaps, each one determining the position and size of its neighbors according to rules that seem to require no external enforcement, and this self-organizing property makes us question whether we truly understand the nature of space itself, or whether space is simply the stage upon which mathematical relationships play out eternally. Imagine standing in a perfectly ordinary four-dimensional space, a realm that exists beyond the three dimensions we inhabit, and within this invisible architecture, there exists a structure so geometrically elegant that it bridges the gap between spheres in ways that seem to defy the spatial intuition we have developed through our entire existence in three dimensions. The Hopf fibration is a mathematical object that takes a three-dimensional sphere, which itself is already a challenging concept for the human mind to fully visualize, and reveals that it is actually composed of infinitely many circles, woven together in such a precise way that each circle is linked with every other circle without ever actually touching or intersecting at any point in space. This linkage pattern is perfect and complete, creating a structure where you could trace your finger along one circle and discover that it threads through the space occupied by all the other circles in a pattern that is simultaneously chaotic and perfectly ordered. The mechanism behind this paradoxical arrangement stems from the fact that when you rotate something in four-dimensional space, the rules governing how shapes can be organized and interlocked become fundamentally different from what our three-dimensional brains expect, allowing for configurations that would be impossible and indeed invisible to us if they were attempted in the space where we live and perceive. The circles themselves, infinite in number and infinitesimal in thickness, are packed so efficiently that they tile the entire three-dimensional sphere without gaps or overlaps, creating a fibration that represents one of the most beautiful and profound connections between topology and geometry that mathematics has yet discovered. What makes this structure so disorienting to contemplate is that despite our inability to see or construct it in our physical reality, its existence is absolutely proven and undeniable, existing in the pure abstract space of four-dimensional geometry where the rules of our sensory experience no longer apply. Yet the mathematics that describes it is as rigorous and unchangeable as any physical law, suggesting that reality contains far more complexity and hidden organization than our limited perceptual apparatus could ever reveal to us. The Hopf vibration also emerges naturally in the mathematics of quantum mechanics and particle physics, where it describes the behavior of spinning particles and their rotational properties in ways that reveal deep connections between abstract geometry and the fundamental nature of reality itself. Imagine a surface that exists in three-dimensional space, yet possesses no distinction between its inside and its outside, a mathematical object that seems to violate the fundamental principle that any closed shape must contain an interior separate from an exterior world, and this surface is called Boy's surface, named after Werner Boy, who first conceived of its existence in 1901 during his doctoral dissertation at the University of Göttingen. The surface presents itself as a singular continuous form that can be traversed without ever crossing a boundary or edge, meaning that an ant crawling across its topology could theoretically walk from what appears to be the outside to what appears to be the inside without ever encountering a barrier or a break in the material structure itself. What makes this paradox so deeply unsettling is that our entire perception of space is built upon the assumption that objects have clear demarcation points, that there exists a fundamental difference between interior and exterior, between self and environment, between the enclosed and the exposed. Yet Boy's surface collapses this distinction into a single unified topology where all points are equally accessible from all other points without crossing any boundary whatsoever. The mathematical mechanism that allows this impossible form to exist involves something called a non-orientable surface, which means that if you were to paint one side of the surface a different color and then follow the surface along its path, you would eventually return to your starting point having painted the entire structure without ever lifting your brush or crossing an edge, suggesting that the surface only truly possesses one side despite occupying space in ways we perceive as having multiple surfaces. The human mind persists in trying to understand Boy's surface by falling back on familiar analogies and visualizations. Yet no matter how many diagrams we study or how many mathematical equations we write, the surface continues to exist in a state of profound contradiction to our intuitive sense of three-dimensional reality, a reminder that the universe contains geometries that our evolved spatial reasoning simply was not designed to comfortably process or fully comprehend. Yet perhaps this very discomfort signals something important, that mathematical truth exists independent of human intuition, and that Boy's surface stands as evidence that reality itself operates according to principles far stranger and more elegant than our everyday experience suggests, inviting us to expand rather than abandon our attempts at understanding. Imagine holding a sphere in your hand, a perfect sphere in three-dimensional space, smooth and symmetrical and utterly familiar to you from childhood onward, yet imagine that this sphere you hold is not actually equivalent to any other sphere of the same size that could exist in the mathematical universe. And imagine further that there exist infinitely many different ways to construct a sphere in higher dimensional spaces that, when reduced to 3 dimensions, produce surfaces that are topologically identical to your ordinary sphere, yet are fundamentally distinct in their structural properties, unable to be continuously deformed into one another without tearing or breaking the fabric of space itself. This is the phenomenon of exotic spheres, discovered in 1956 by John Milner, and they represent a profound violation of our intuitive understanding that a sphere is simply a sphere, that geometry is absolute and unchanging across mathematical dimensions. The exotic sphere emerges from the mathematics of differential topology, a field that distinguishes between the smooth structure of a space and its merely topological properties, asking not just what shape something is, but how many fundamentally different ways that shape can be smoothly constructed in higher dimensions. And the answer, shockingly, is that in dimensions greater than 3, there are infinite families of distinct smooth structures that all correspond to the same topological sphere. When we examine our everyday three-dimensional reality, this paradox feels particularly disorienting because the exotic spheres primarily exist as mathematical objects in dimensions 7 and higher. Yet their existence proves that our intuition about spheres as unique and fundamental shapes is incomplete and constrained by the limited dimensionality we inhabit. The psychological mechanism that allows this paradox to persist is that we have fundamentally confused the map with the territory, treating our visual and tactile experience of spheres as if it represents all possible spheres rather than merely the spheres that naturally occur in our three-dimensional neighborhood, much like someone who has only ever seen circles drawn on paper might struggle to understand that three-dimensional spheres cannot be perfectly drawn as flat images. And we have normalized this confusion by never questioning whether the sphere we imagine is truly universal or merely parochial to our dimension. Imagine a three-dimensional space that appears completely normal at first glance, a geometric object that seems indistinguishable from ordinary three-dimensional Euclidean space when you examine any finite region of it, yet possesses a fundamental structural property that makes it impossible to smoothly deform back into standard space without tearing or breaking something at infinity. This is the Whitehead manifold, a topological construct named after mathematician John Henry Constantine Whitehead, and it represents one of the most unsettling paradoxes in geometric mathematics, because it asks us to confront the idea that two spaces can be locally identical in every measurable way while remaining globally incompatible. The Whitehead manifold is constructed through an infinite sequence of operations, beginning with three-dimensional space and systematically removing and reattaching solid tori, those donut-shaped geometric forms, in increasingly intricate patterns that spiral outward toward infinity. At each stage of this construction, if you were to examine any finite neighborhood, any bounded region of the manifold, you would observe a structure entirely consistent with normal Euclidean space, finding no anomalies, no discontinuities, no suggestions that anything unusual had occurred during the construction process. Yet despite this local equivalence, the global topology of the Whitehead manifold differs fundamentally from standard space, creating a kind of geometric amnesia where the object cannot remember how to return to its original form. The psychological mechanism underlying our difficulty in accepting the Whitehead manifold stems from our intuitive belief that if something looks and behaves identically to something else in every observable way, then it must ultimately be the same thing, a principle that works flawlessly in the finite, bounded world we inhabit, but collapses spectacularly when infinity enters the picture. We have been conditioned by experience to assume that local properties determine global properties, that if every part of a system is identical to a reference system, then the whole must be identical as well, yet the Whitehead manifold serves as a counterexample that shatters this assumption with quiet elegance. The manifold demonstrates that topological properties, the fundamental structural characteristics of space itself, can diverge completely from what any finite examination would predict, suggesting that our inability to perceive or access infinity leaves us with only partial information about the geometry surrounding us.